Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's deep past long before the first whisper of what we might call civilization. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, Earth breathes its first breath. Though no lungs exist to receive it, the planet exhales methane, ammonia, and water vapor from countless volcanic throats, while cosmic debris still rains down like a slow, eternal storm. This early atmosphere bears no resemblance to the air that fills human lungs. Today it would kill any complex life instantly, yet it cradles the planet in a greenhouse warmth that will prove essential for what follows. The very molecules that spell death for modern organisms nurture the chemical pathways that will eventually lead to life's emergence. The young Earth spins faster then, completing each day in perhaps 6 hours, while the moon hangs impossibly close, nearly 3 times closer than it hovers today, raising tides that sweep hundreds of miles inland twice each brief day. These tidal surges carry more than water. They transport minerals, organic compounds, and electrical charges across vast distances, mixing and concentrating the building blocks of future life in tidal pools that stretch across entire continents. Only there are no true continents yet, just scattered volcanic islands poking through a global ocean that covers nearly everything. The sun burns dimmer in this ancient sky, providing roughly 30% less energy than it delivers to modern Earth. Yet the thick atmosphere traps heat so efficiently that surface temperatures remain warm enough to keep water liquid. This faint young sun paradox puzzles scientists. Still, how does a cooler star maintain a warm planet? The answer lies partly in atmospheric composition, partly in planetary dynamics, and partly in processes that remain tantalizingly unclear even to modern geochemistry. Lightning forks through this alien sky with a frequency that modern Earth has forgotten, each bolt carrying electrical potential through gases that react in ways no living thing has ever witnessed. Thunder rolls continuously across the planetary surface, not from isolated storms but from the constant electrical discharge of an atmosphere learning to stabilize itself. Each lightning strike synthesizes organic compounds from simple gases, amino acids, nucleotides, fatty acids. The molecular alphabet of life, forming letter by letter in the sky itself, before raining down into warm, shallow seas like chemical snow. Scientists call this the Hadean Eon, named for Hades, though the hellish comparison misses something essential about this time. This is not destruction, but the slow, patient construction of possibilities. Every volcanic eruption contributes sulfur compounds and trace metals that will prove essential for enzymatic processes billions of years in the future. Every lightning strike creates molecules that will eventually learn to replicate themselves. Every meteorite impact delivers water, organic compounds, and rare elements from across the solar system, turning Earth into a cosmic repository of chemical potential. The atmosphere itself becomes a vast chemical laboratory, but one that operates on timescales that dwarf human imagination. Reactions that modern chemists complete in seconds or minutes unfold across millennia here, as dilute concentrations of reactants drift through three-dimensional space, occasionally encountering each other in productive combinations. The entire planet serves as a reaction vessel, stirred by tidal forces, heated by volcanic activity, and energized by cosmic radiation streaming through the thin ozone layer. Perhaps the greatest mystery lies not in what happens during these early eons, but in what doesn't happen. The chemistry exists. The energy flows constantly. The raw materials accumulate in vast abundance, yet life waits. For hundreds of millions of years, Earth assembles all the necessary components while something ineffable holds back the spark of self-replication. Modern biochemists can synthesize many of life's building blocks in laboratory conditions that mimic early Earth. Yet the transition from chemistry to biology remains one of science's most profound puzzles. The iron in Earth's core still settles toward the center during these early ages, generating magnetic fields that fluctuate wildly as the planet learns to protect itself from solar radiation. These early magnetic fields reverse themselves frequently, sometimes multiple times per million years, creating aurora displays that paint the sky in colors no human eyes will ever witness. Metallic rain falls from impact-vaporized asteroids, enriching surface waters with elements like molybdenum, tungsten, and platinum that will prove essential for biological processes still unimaginable. Continents begin as nothing more than floating scum-lighter, silicate minerals that rise to the surface of a largely molten planet and congeal into the first stable land masses. These proto-continents drift across the surface like islands of cooled slag, colliding, merging, and breaking apart in patterns that establish the fundamental rhythm of plate tectonics. The very ground shifts and reforms as heavier materials sink and lighter ones rise, like a vast, slow-motion sorting of cosmic ingredients that will continue for billions of years. Water arrives from multiple sources during these early times, some locked within the minerals of accreting planetesimals, some delivered by comets and asteroids from the outer solar system, some outgassed from volcanic activity deep within the planet. The early oceans taste nothing like modern seawater. They contain far more dissolved metals, different salt concentrations, and chemical gradients that create layers of distinct composition stacked like liquid geological strata. Temperature gradients in these early oceans create convection currents that transport dissolved materials across enormous distances, establishing circulation patterns that will persist, in modified form, throughout Earth's history. Hot springs and hydrothermal vents dot the ocean floor, creating localized environments where temperatures, pressures, and chemical concentrations differ dramatically from the surrounding water. These become natural laboratories where more complex chemistry can unfold, protected from the diluting effects of the vast ocean. The boundary between ocean and atmosphere proves surprisingly active during these early times. Wave action, powered by the close moon and rapid planetary rotation, creates foam and spray that carries dissolved minerals high into the atmosphere, where they participate in gas phase chemistry before falling back as aerosols. This constant exchange between liquid and gas phases accelerates certain chemical processes while inhibiting others, creating a planetary scale selection pressure that favors some molecular forms over others. And, through it all, the planet waits, not with consciousness, but with the patience of stone and gas and slowly cooling metal. Every process unfolds at its own necessary pace, building toward complexities that will not emerge for nearly 1 billion years, preparing foundations for civilizations that remain almost 4 billion years in the future. The carbon cycle begins its slow dance between atmosphere, ocean, and rock. The nitrogen cycle starts its patient transformation of atmospheric gas into biologically useful compounds. The phosphorus cycle commences its essential work of concentrating this vital element in locations where it can eventually nourish living systems. Earth takes its first breath, exhales into empty space, and begins the longest conversation in the solar system's history, a chemical dialogue that will eventually include biology, geology, and atmospheric science in an intricate dance of planetary evolution. The stage is set. The players are assembled at the molecular level, and the drama of life on Earth prepares to begin its first tentative scene. Only the curtain will not rise for another several 100 million years, giving time for every prop, every backdrop, every subtle detail to achieve perfect readiness. When stones learn chemistry, they do so with the patience of minerals that have waited 4 billion years for their moment. In tide pools scattered across volcanic coastlines, clay particles begin to demonstrate an unexpected talent. They can organize organic molecules into patterns that persist longer than random chance would allow. The Montmorillonite clays, formed from weathered volcanic ash, develop surfaces that attract amino acids and nucleotides like molecular magnets, concentrating them into configurations that begin to resemble the blueprints of life. These clay templates do not create life directly, but they provide something equally essential, a stable platform where chemistry can become more than the sum of its random collisions. RNA molecules, those ancient cousins of DNA, find that certain clay surfaces help them fold into shapes that can catalyze their own replication. The stones become teachers, demonstrating through their crystalline structure how information can be stored in molecular arrangements and passed from one generation to the next. The transition from lifeless chemistry to self-replicating systems unfolds not in a single dramatic moment, but across tens of millions of years of molecular trial and error. Early protocells form as lipid membranes spontaneously organize around collections of self-catalyzing RNA, creating the first boundaries between internal and external chemistry. These primitive cells lack almost everything that defines modern life: no DNA, no proteins, no sophisticated metabolic pathways. Yet they possess the fundamental ability to make copies of themselves, imperfectly but persistently. Deep beneath the ocean's surface, hydrothermal vents create pocket universes where the normal rules of chemistry bend toward possibilities that the open ocean cannot support. Here, in eternal darkness, lit only by the dim glow of mineral-rich water meeting seawater, temperatures and pressures create conditions that favor the formation of complex organic molecules. Iron-sulfur clusters, formed naturally in these environments, begin to demonstrate enzymatic properties that will later be incorporated into the metabolic pathways of all living things. The chemical signature of these early life forms proves surprisingly difficult to detect in rocks that have survived nearly 4 billion years of geological processing. Scientists search for isotopic ratios that suggest biological activity, carbon isotopes that show the preferences of early metabolic processes, sulfur isotopes that indicate bacterial processing of seawater chemistry. The evidence remains tantalizingly indirect, like trying to reconstruct a conversation from echoes that have bounced off canyon walls for geological ages. Perhaps most remarkably, life's earliest forms seem to have solved problems that still challenge modern biochemistry. They developed methods for harvesting energy from chemical gradients, processing toxic metals, and surviving in environments that would sterilize any modern organism. These ancient microbes created the first biological fuel cells, extracting energy from the reaction between iron and sulfur compounds in ways that modern biotechnology is only beginning to understand. The atmosphere during these early experiments remains utterly hostile to complex life as we know it. Methane and ammonia dominate the gas mixture, while oxygen exists only in trace amounts produced by the photolysis of water vapor in the upper atmosphere. This reducing atmosphere actually favors certain types of organic chemistry, allowing carbon compounds to remain stable in forms that would instantly oxidize in modern air. Life begins not despite the hostile atmosphere, but because of it. Early photosynthetic systems develop in shallow waters where sunlight can penetrate. But these primitive solar collectors bear little resemblance to modern photosynthesis. Instead of splitting water molecules to release oxygen, they extract electrons from hydrogen sulfide, iron compounds, or organic molecules, releasing sulfur or other byproducts instead of the oxygen that will later transform the planet. These anoxygenic photosynthetic systems demonstrate that life can harness solar energy through multiple pathways, not just the single route that modern plants have perfected. The mystery of life's origin deepens rather than clarifies as scientists develop more sophisticated methods for studying early Earth chemistry. Laboratory experiments can create many of life's building blocks under simulated early Earth conditions. Yet the gap between complex organic chemistry and true self-replication remains as puzzling as ever. Something about the transition from chemistry to biology continues to elude complete understanding, as if life's emergence required a combination of circumstances too intricate for laboratory reproduction. Continental drift during these early ages creates and destroys potential habitats for emerging life with a frequency that modern continents have forgotten. Volcanic island chains rise and fall. Shallow seas open and close. Hydrothermal systems activate and shut down as the solid Earth continues its restless rearrangement. Life must be portable during these times, capable of surviving the destruction of entire ecosystems and recolonizing new habitats as they become available. The first genetic codes emerge not as the sophisticated system that modern life employs, but as simpler arrangements that can encode basic information about molecular structure and function. These early codes may have used different amino acids, different base pairs, even different numbers of coding units per genetic word. The universal genetic code that unites all modern life represents not life's first attempt at information storage, but perhaps its most successful experiment after millions of years of molecular evolution. Temperature regulation becomes one of early life's most crucial innovations, though not in the way modern organisms maintain stable internal temperatures. Instead, early microbes learn to modify their local chemistry to create more favorable conditions, concentrating nutrients, adjusting pH levels, creating microscopic environments that differ significantly from the surrounding ocean. These biochemical niches become the first ecosystems, tiny pockets of modified chemistry maintained by the metabolic activity of their inhabitants. The chemical pathways that early life develops prove remarkably conserved across geological time. Modern organisms still employ many of the same fundamental biochemical processes that evolved during these ancient ages: electron transport chains, carbon fixation pathways, metal-binding proteins. Life's earliest experiments in energy harvesting and molecule building establish patterns that will persist for billions of years, suggesting that certain chemical solutions to biological problems represent optimal arrangements that later evolution cannot improve upon. And still, through these momentous chemical discoveries, Earth maintains its patient pace. Each breakthrough in molecular organization unfolds across millions of years. Each new metabolic pathway requires geological ages to refine and perfect. The stones continue their chemistry lessons with the thoroughness that only minerals can demonstrate, teaching organic molecules the fundamental principles of structure, stability, and self-organization that will guide the development of increasingly complex life forms. The first ecosystems consist of nothing more than thin films of microbes coating rock surfaces in tidal zones. Yet these simple communities establish the basic principles of ecological interaction that will govern all future biological communities. Producer organisms harvest energy from sunlight or chemical gradients, while decomposer organisms recycle organic molecules back into their constituent elements. The great cycles of life, carbon, nitrogen, sulfur, phosphorus begin their eternal circulation through living and non-living systems. The great poisoning begins not with malice, but with the innocent exhalation of organisms that have discovered how to split water molecules and steal their electrons for photosynthesis. Cyanobacteria, Earth's first oxygen-producing life forms, emerge in shallow coastal waters roughly 2.5 billion years ago and immediately begin the most devastating pollution event in planetary history. They release oxygen gas as a waste product of their metabolism, unaware that this highly reactive molecule will prove toxic to nearly every other form of life that has evolved during Earth's first 2 billion years. Oxygen burns through the reducing atmosphere like molecular fire, combining with methane to form carbon dioxide and water, reacting with ammonia to create nitrogen gas, and most catastrophically, penetrating the ocean depths where it begins to oxidize dissolved iron. The seas, which have remained a rusty green color for billions of years due to dissolved ferrous iron, suddenly begin to clear as iron atoms bind with oxygen and precipitate out as insoluble red oxides. These banded iron formations, alternating layers of red and black minerals, record the slow strangulation of an entire biosphere in geological strata that will persist for billions of years. The transition proves neither swift nor uniform across the planet's surface. Oxygen accumulates gradually, held in check for hundreds of millions of years by the vast reservoir of reduced chemicals in ocean and atmosphere that eagerly consume each molecule of this reactive gas. Continental weathering accelerates as oxygen attacks rock surfaces, releasing nutrients into rivers and ocean basins while simultaneously removing carbon dioxide from the atmosphere through the formation of carbonate minerals. The entire planetary chemistry shifts toward oxidation, like a cosmic chemical reaction proceeding in slow motion across geological time. Most of Earth's existing life forms face extinction during this great oxygenation event, unable to cope with a gas that attacks their cellular machinery and destroys their carefully balanced metabolic processes. Anaerobic bacteria retreat to oxygen-free environments, deep sediments, hot springs, the guts of future animals where they will persist as evolutionary relics of Earth's ancient chemistry. Only organisms that can neutralize oxygen's toxic effects, or better yet, harness its reactive power for energy production, survive this planetary transformation. The irony proves exquisite in its thoroughness. Cyanobacteria, the organisms responsible for oxygen pollution, also become among its first victims as their own waste product begins to poison the very environments where they evolved. Many species of early photosynthetic bacteria vanish from the fossil record during this period, apparently unable to adapt to the oxygen-rich conditions they themselves created. Evolution begins its long lesson in unintended consequences, demonstrating how successful life forms can engineer their own obsolescence through their very success. Atmospheric oxygen concentrations rise slowly, requiring nearly 1 billion years to reach levels that would support complex multicellular life. During this prolonged transition, the planet experiments with intermediate atmospheric compositions that have no modern analog. Oxygen levels fluctuate dramatically, sometimes approaching modern concentrations before falling back to near zero levels, creating a planetary respiratory rhythm that governs the pace of evolutionary innovation for hundreds of millions of years. The protective ozone layer forms as a byproduct of oxygen accumulation, creating a chemical shield that blocks harmful ultraviolet radiation and allows life to venture into previously uninhabitable surface waters. This invisible atmospheric barrier transforms the ocean's upper layers from a sterile, radiation-blasted zone into prime real estate for photosynthetic organisms. Life begins to stratify vertically in the water column, with different species occupying distinct depth zones based on their tolerance for light, oxygen, and ultraviolet radiation. Deep ocean chemistry undergoes equally dramatic transformation as oxygen penetrates marine sediments and begins to alter the fundamental processes of decomposition and nutrient cycling. Sulfate-reducing bacteria, which have dominated deep-sea metabolism for billions of years, find their habitats shrinking as oxidizing conditions spread through previously anoxic environments. The boundary between oxidized and reduced environments becomes a dynamic frontier that migrates through ocean basins like a slow-motion chemical weather system. Continental surfaces begin to change color during this great atmospheric transition. Red beds, sedimentary rocks colored by iron oxides, appear in the geological record for the first time, marking landscapes where oxygen has penetrated soil and groundwater systems. These rusty continental surfaces contrast sharply with the gray and green rocks of earlier ages, creating a visual signature of planetary oxygenation that remains visible in stone formations billions of years later. The mystery of oxygen's early fate continues to puzzle geochemists who study this ancient atmospheric revolution. Calculations suggest that early oxygen production should have overwhelmed the planet's capacity to consume this reactive gas much more quickly than the geological record indicates. Something about early Earth's chemistry was apparently more efficient at neutralizing oxygen than modern models predict, perhaps involving biological processes or chemical reactions that have left no clear trace in surviving rocks. Photosynthetic efficiency improves dramatically during this period as cyanobacteria perfect the molecular machinery of water-splitting photosynthesis. These organisms develop sophisticated light-harvesting complexes that can capture solar energy across multiple wavelengths, extracting maximum power from sunlight while minimizing damage from intense ultraviolet radiation. The biochemical pathways they establish become the foundation for all future plant photosynthesis, remaining essentially unchanged for over 2 billion years. Trace metal availability in ocean water shifts dramatically as oxygen alters the solubility and transport of elements essential for biological processes. Copper, zinc, and molybdenum become more readily available in oxidized seawater, enabling the evolution of new enzymatic processes that will prove crucial for complex life. Conversely, iron becomes much less available as it precipitates out of solution, forcing life to develop more sophisticated methods for acquiring and storing this essential element. The global carbon cycle undergoes fundamental reorganization as atmospheric composition shifts from methane-dominated to carbon dioxide-dominated chemistry. Organic carbon burial increases dramatically during this period, as dead organisms can now be preserved in oxygen-free sediments rather than being completely decomposed by anaerobic bacteria. These buried carbon reserves represent the beginning of Earth's vast fossil fuel deposits, stockpiling solar energy that will not be released until human civilization learns to burn coal and oil billions of years in the future. Temperature regulation becomes increasingly important as changing atmospheric composition alters the planet's greenhouse gas concentrations. Methane, a potent greenhouse gas, virtually disappears from the atmosphere as oxygen destroys it through chemical reactions. Carbon dioxide concentrations fluctuate wildly as the carbon cycle adjusts to new chemical conditions. Ice ages and greenhouse periods alternate with increasing frequency as the climate system learns to operate under oxidizing conditions. And through this greatest of all environmental catastrophes, life demonstrates its fundamental resilience and adaptability. New forms of cellular respiration evolve that can harness oxygen's reactive power for energy production, turning the great poison into the great fuel that will power all future complex life. Mitochondria. The cellular powerhouses of modern organisms trace their ancestry to bacteria that learned to breathe oxygen during this ancient atmospheric crisis. The great poisoning continues for hundreds of millions of years, proceeding with the patience of planetary chemistry operating on geological time scales. Each increment of atmospheric change requires vast ages to stabilize. Each evolutionary innovation demands millions of years to refine and perfect. Earth exhales its ancient atmosphere and slowly learns to breathe the oxygen-rich air that will sustain dinosaurs, forests, and eventually, human civilization. A billion years of waiting begins, stretching across geological time like a held breath between Earth's early experimental phase and its eventual explosion into complex life. Scientists call this the boring billion, a span of time longer than the entire history of complex multicellular organisms, during which life seems to plateau in forms so simple they barely register in the fossil record. Yet, beneath this apparent stagnation, the planet undertakes fundamental renovations that will make all future complexity possible. Atmospheric oxygen stabilizes at levels far below modern concentrations, hovering around 1 to 10% of current atmospheric composition. This intermediate oxygen state proves neither high enough to support large multicellular organisms nor low enough to permit the return of ancient anaerobic ecosystems. Life exists in a chemical purgatory, equipped with the molecular machinery to handle oxygen's toxicity, but lacking sufficient atmospheric fuel to power the energy-intensive processes that complex multicellularity will eventually require. Continental drift proceeds with unprecedented stability during these Middle Ages of Earth history. Supercontinents form and persist for hundreds of millions of years, creating vast interior regions isolated from oceanic influence where unique geological processes can unfold without interruption. The supercontinent Rodinia assembles itself grain by grain across 200 million years, gathering most of Earth's landmass into a single, enormous continent surrounded by a global ocean of unprecedented size and chemical uniformity. Eukaryotic cells, those complex cellular forms that will eventually give rise to plants, animals, and fungi, make their first tentative appearance during this prolonged period of apparent biological stasis. These early eukaryotes represent one of evolution's most momentous innovations, yet they remain microscopic and relatively uncommon for hundreds of millions of years. The merger of different bacterial species into the first eukaryotic cells requires not just the right chemical conditions, but also the kind of evolutionary patience that only geological time can provide. Ocean chemistry stabilizes into patterns that will persist, with minor variations, for the remainder of Earth's history. The great iron formations cease their accumulation as dissolved iron finally disappears from seawater, leaving behind banded deposits that record the planet's transition from a reducing to an oxidizing world. Sulfate concentrations in seawater increase dramatically as continental weathering accelerates under oxygen-rich atmospheric conditions, providing new energy sources for deep-sea bacterial communities. The mystery of this billion-year pause in evolutionary innovation continues to puzzle biologists who study the deep history of life on Earth. All the chemical ingredients for complex multicellular organisms exist during this period: stable oxygen levels, diverse nutrients, energy-rich environments, yet life seems reluctant to experiment with larger, more sophisticated forms. Perhaps the energetic costs of multicellularity remain too high, or perhaps the evolutionary pathways toward complexity require chance discoveries that simply take hundreds of millions of years to stumble upon. Carbon isotope ratios in rocks from this period suggest that biological productivity remains relatively low and stable throughout these Middle Ages of Earth history. Primary production in ancient oceans appears to have reached a steady state where photosynthetic organisms produce organic matter at rates that exactly balance decomposition and burial. This biological equilibrium creates a planetary metabolism that hums along quietly for geological ages without major innovations or catastrophes. Mountain building proceeds at a leisurely pace during this period of continental stability, creating ranges that rise and erode over timescales that dwarf the dramatic tectonics of more recent geological ages. The slow collision of continental fragments builds the Grenville Mountains across eastern North America, a process that requires 200 million years to complete and produces some of the most ancient rocks still exposed at Earth's surface. These mountains weather away almost as slowly as they rise, feeding sediments into river systems that meander across stable continental interiors. Volcanic activity continues throughout this period, but lacks the catastrophic intensity that characterizes other geological eras. Large igneous provinces, vast outpourings of basaltic lava still form occasionally, but they seem to have little impact on global climate or biological systems. The planet appears to have developed a kind of geological steady state where tectonic processes proceed smoothly without the dramatic perturbations that mark other periods of Earth history. Microbial ecosystems during this time develop increasing sophistication within their microscopic scale limitations. Bacterial communities form complex layered structures called stromatolites that can reach several meters in height, creating the first biological architecture on a scale visible to hypothetical human observers. These living rock formations demonstrate that even simple organisms can engage in ecosystem engineering, modifying their physical environment to create more favorable conditions for their own survival and reproduction. Atmospheric composition remains surprisingly stable throughout this billion-year span, with oxygen, carbon dioxide, and nitrogen concentrations fluctuating within narrow ranges that suggest some form of planetary regulation. Whether this stability results from geological buffering, biological feedback, or simple chemical equilibrium remains unclear. But the result is a planet that maintains relatively constant surface conditions for an almost incomprehensibly long period of time. Sexual reproduction evolves during these Middle Ages, though its early forms bear little resemblance to the elaborate mating behaviors of modern organisms. Early eukaryotes begin exchanging genetic material through simple fusion processes that allow beneficial mutations to spread through populations more rapidly than asexual reproduction would permit. This innovation in genetic exchange will eventually prove crucial for the evolution of complex multicellular organisms, but its immediate effects remain subtle and difficult to detect in the fossil record. The slow evolution of cellular complexity proceeds through countless incremental improvements in molecular machinery, mitochondria and chloroplasts. The bacterial symbionts that power eukaryotic cells gradually integrate more completely with their host cells, developing specialized functions and losing genes that are no longer necessary for independent survival. This molecular domestication process unfolds over hundreds of millions of years, creating the efficient cellular powerhouses that will eventually fuel multicellular life. Global climate during this period shows remarkable stability, with surface temperatures apparently remaining within narrow ranges that prevent the extreme ice ages and greenhouse periods that characterize other geological eras. Ocean circulation patterns establish themselves and persist for hundreds of millions of years, creating stable chemical gradients that allow marine ecosystems to develop increasing complexity within their microscopic scale limitations. And still the planet waits, not with impatience but with the thorough preparation that only geological time can provide. Every chemical cycle refines itself through countless iterations. Every biological innovation undergoes millions of years of testing and optimization. Every physical process establishes the stable patterns that will eventually support the incredible diversity of life forms waiting in Earth's future. The boring billion proves anything but boring when viewed from the perspective of planetary preparation. like a master craftsman spending years sharpening tools and preparing materials before beginning a masterpiece. Earth uses this prolonged period to establish all the foundational systems that complex life will require: continental drift, atmospheric chemistry, ocean circulation, biological metabolism. All these planetary processes achieve a level of stability and sophistication that will soon permit experiments in multicellular organization that were simply impossible during Earth's earlier, more chaotic phases. The wait continues with geological patience, each year adding microscopic refinements to systems that will eventually support forests, coral reefs, and human civilizations. The planet inhales slowly, preparing for the explosive diversification that will transform Earth from a world of microscopic organisms into a biosphere of stunning complexity and beauty. Snowball. Earth's silence descends across the planet not once, but repeatedly, as global glaciation events grip the world in ice that stretches from pole to equator sometime between 750 and 580 million years ago. The oceans freeze to depths of over a kilometer in places, while continental ice sheets advance across tropical latitudes that will never again experience such cold. This is not the gradual cooling of ordinary ice ages, but a catastrophic transition into a planetary deep freeze that transforms Earth into a giant snowball spinning through space, reflecting most of the sun's energy back into the cosmic darkness. The triggers for these extreme glaciation events remain puzzling to paleoclimatologists who study this ancient frozen world. Continental configurations during the late Proterozoic create unusual patterns of ocean circulation and atmospheric heat transport that may predispose the planet to runaway cooling. Once ice sheets begin advancing toward the equator, they reflect increasing amounts of solar radiation back to space, creating a positive feedback loop where cooling begets more cooling until even tropical oceans succumb to freezing temperatures. Volcanic carbon dioxide continues seeping into the atmosphere throughout these frozen epochs, but its warming effect proves insufficient to counteract the planet's enhanced reflectivity. Ice and snow cover reflect up to 90% of incoming solar radiation, compared to the 10 to 20% reflected by normal ocean and land surfaces. Earth becomes a cosmic mirror, bouncing the sun's warmth back into space while slowly accumulating the volcanic greenhouse gases that will eventually trigger its escape from this icy prison. Life persists during these global glaciations, though in forms and locations that challenge our understanding of biological resilience. Thin films of liquid water may survive between ice and rock surfaces, warmed by geothermal heat and protected from complete freezing by pressure and dissolved minerals. Hydrothermal vents on the deep ocean floor continue operating beneath kilometers of ice, creating oases of liquid water and chemical energy in an otherwise frozen world. Microscopic organisms huddle in these refugia, maintaining the thread of biological continuity through Earth's most severe climate crisis. The duration of individual snowball episodes stretches across millions of years, far longer than any ice age in Earth's more recent history. Some estimates suggest that individual glaciation events may persist for 10 to 15 million years before volcanic carbon dioxide accumulates to levels sufficient to begin melting the global ice cover. During these prolonged frozen periods, evolution essentially pauses as ecosystems shrink to tiny pockets of habitat scattered across an otherwise sterile planet. Ocean chemistry beneath the ice undergoes dramatic changes as normal circulation patterns shut down and biological productivity nearly ceases. Without photosynthetic organisms consuming carbon dioxide and producing oxygen, seawater becomes increasingly acidic and oxygen depleted. Iron concentrations rise dramatically as reduced conditions return to ocean basins that had been oxidized for hundreds of millions of years. The chemical signatures of these altered ocean conditions persist in rock formations that record this ancient frozen world. A continental weathering slows to nearly zero during snowball episodes, as rock surfaces disappear beneath kilometers of ice and snow. The normal processes that regulate atmospheric carbon dioxide through the breakdown of silicate minerals essentially shut down, allowing volcanic emissions to accumulate unchecked in the atmosphere. This geological thermostat, which normally maintains Earth's climate within habitable bounds, becomes disabled by the very ice it would normally prevent from forming. The escape from snowball conditions proves as dramatic as the initial freezing, though it unfolds over geological rather than human timescales. As atmospheric carbon dioxide reaches levels perhaps 100 times higher than modern concentrations, the enhanced greenhouse effect finally overpowers Earth's ice-enhanced reflectivity. Surface temperatures begin rising rapidly, triggering catastrophic melting that can transition the planet from completely frozen to ice-free conditions within perhaps a few thousand years. These rapid deglaciation events create some of the most unusual rock formations in Earth's geological record. Cap carbonate's thick layers of limestone and dolomite form immediately after each snowball episode, as the super-greenhouse conditions following deglaciation cause massive precipitation of carbonate minerals from carbon dioxide-saturated seawater. These distinctive rock layers provide some of the clearest evidence that extreme glaciation events actually occurred during this ancient period. The biological consequences of repeated snowball episodes prove both devastating and ultimately beneficial for the evolution of complex life. Most microbial ecosystems suffer severe population bottlenecks during glaciation events, reducing global biodiversity to small refugial populations that must subsequently recolonize the entire planet during interglacial periods. These cycles of near extinction and rapid recolonization may accelerate evolutionary innovation by repeatedly selecting for organisms capable of surviving extreme environmental stress. Atmospheric oxygen levels fluctuate dramatically during and after snowball episodes as the normal biological processes that regulate atmospheric composition shut down and restart repeatedly. Some models suggest that oxygen concentrations may drop to near zero levels during the most severe glaciation events, then spike to higher than normal levels during the subsequent biological recovery periods. These atmospheric oscillations create selection pressures that may favor the evolution of more sophisticated cellular machinery for handling variable oxygen concentrations. The mystery of how life not only survives, but apparently thrives in the aftermath of these global catastrophes continues to intrigue evolutionary biologists. Fossil evidence suggests that the diversity and complexity of microbial life actually increases following each snowball episode, as if the extreme environmental stress somehow stimulates rather than inhibits evolutionary innovation. Perhaps the near-death experience of global glaciation breaks through evolutionary stasis and opens new adaptive possibilities that would remain unexplored under more stable conditions. Sedimentary rocks deposited during snowball episodes preserve evidence of unusual chemical conditions that have no modern analog. Deposits of glacial sediments in tropical latitudes contain unusual mineral assemblages and isotopic signatures that record the extreme environmental conditions of a frozen Earth. Some of these rocks preserve chemical fossils, molecular biomarkers that suggest life forms during this period developed biochemical adaptations that have since been lost from the evolutionary record. The thermal inertia of such massive ice sheets means that even after atmospheric conditions become favorable for melting, the physical process of deglaciation requires thousands of years to complete. During this transition period, Earth experiences climate conditions unlike anything in its more recent history. Extreme greenhouse atmospheric compositions combined with massive ice sheets that continue melting for millennia. These transitional periods may provide unique evolutionary opportunities for organisms that can exploit the unusual environmental conditions. Global ocean circulation patterns during snowball episodes remain largely mysterious, though computer models suggest that some form of thermohaline circulation may persist beneath the ice cover. Dense, cold water continues sinking in polar regions, while warmer water from hydrothermal sources creates slow convection currents that transport nutrients and dissolved gases through the ice-covered ocean basins. These sluggish circulation patterns maintain minimal chemical gradients that allow deep-sea ecosystems to persist through the frozen epochs. And through these ultimate tests of planetary endurance, Earth demonstrates the resilience of its life-supporting systems. Even when pushed to the very brink of becoming a permanently frozen world, the planet retains the geological and atmospheric mechanisms necessary to restore habitable conditions. The carbon cycle continues operating, albeit at reduced rates. Plate tectonics persists, maintaining the volcanic outgassing that eventually breaks the ice's grip on global climate. The silence of Snowball Earth proves deceptive, masking intense geological and biological activity beneath its frozen surface. Evolution continues in hidden refugia, preparing for the explosive diversification that will follow the final deglaciation. The planet sleeps beneath its icy blanket, dreaming of the complex multicellular life forms that will soon emerge to populate its warming oceans. The Ediacaran garden blooms in Earth's ancient seas roughly 570 million years ago, revealing life forms so strange and beautiful that modern science struggles to understand their place in the story of evolution. These are not the familiar shells and skeletons that will define later fossil assemblages, but soft-bodied organisms that appear like living quilts stitched from tissue and filled with mysterious internal geometries. They carpet the seafloor in shallow marine environments across the globe, creating Earth's first experiment with large, complex multicellular life, Dickinsonia. Perhaps the most enigmatic of these ancient creatures, grows to over a meter in length, yet possesses no apparent mouth, gut, or any recognizable organ system. Its body consists of repeated segments that expand in mathematical progression, creating a form that seems more like a living mathematical equation than anything recognizable as an animal. The creature appears to have absorbed nutrients directly through its skin while gliding across microbial mats that covered the Ediacaran seafloor, grazing on bacterial communities like a biological lawnmower operating in ultra-slow motion. These early complex organisms inhabit a world still largely devoid of predation, where the primary challenge involves gathering sufficient nutrients and energy rather than avoiding being eaten. The absence of shells, spines, or any apparent defensive structures in Ediacaran fossils suggests a peaceful world where competition occurs through more subtle mechanisms than the arms races that will characterize later evolutionary periods. Organisms spread across available habitat like biological carpets, each species claiming its particular niche in the three-dimensional mosaic of ancient seafloor communities. Charnia, one of the most abundant Ediacaran organisms, resembles a fern or feather anchored to the seafloor by a holdfast structure that may represent evolution's first experiment with complex attachment mechanisms. Its frond-like body extends into the water column to capture dissolved nutrients or tiny particles of organic matter, pioneering the filter-feeding lifestyle that will become crucial for many later marine ecosystems. The branching, fractal geometry of Charnia's body maximizes surface area for nutrient absorption while minimizing the metabolic costs of maintaining large body size. The mystery of Ediacaran body plans deepens as paleontologists discover increasingly bizarre forms that seem to violate basic principles of animal architecture. Tribrachidium possesses three-fold radial symmetry, a body plan so unusual that no living organism employs it today. Sprigina displays what appears to be a head-like structure and segmented body, yet lacks any trace of the nervous system or sensory organs that such organization would seem to require. These organisms seem to represent evolutionary experiments that led nowhere, dead-end innovations in the history of complex life. Atmospheric oxygen concentrations during the Ediacaran period fluctuate dramatically, creating environmental conditions that favor certain types of metabolism while constraining others. These oxygen oscillations may explain why Ediacaran organisms develop such unusual body plans. They represent adaptations to atmospheric chemistry that will never again occur in Earth's history. Large, flat body forms with high surface area to volume ratios may allow efficient gas exchange in an atmosphere with unstable oxygen levels. The Ediacaran seafloor itself differs dramatically from modern marine environments, lacking the bioturbation, the mixing and churning of sediments by burrowing animals that characterizes later periods. Sediments accumulate in undisturbed layers, preserving delicate impressions of soft-bodied organisms with a fidelity that will become impossible once animals learn to burrow. These pristine sedimentary conditions create a unique preservational window that captures details of soft tissue organization rarely visible in later fossil assemblages. Microbial mats continue to dominate many Ediacaran environments, creating living carpets of bacteria and archaea that stretch across vast areas of shallow sea floor. These mats provide both substrate and food source for early complex life, establishing some of Earth's first examples of ecosystem engineering, where large organisms modify their physical environment to create more favorable living conditions. The interaction between mat-forming microbes and grazing macroorganisms begins the complex ecological relationships that will characterize all future biological communities. The Ediacaran period witnesses the first appearance of trace fossils, tracks, trails, and burrows that record animal behavior rather than body parts. These traces suggest that some organisms possessed the neuromuscular coordination necessary for directed movement, though the simplicity of most Ediacaran traces indicates nervous systems far less sophisticated than those of later animals. Simple, meandering trails record the movement of organisms across microbial mats, while rare burrow structures suggest that a few species had begun to explore the three-dimensional habitat possibilities offered by soft sediments. Sexual reproduction, if it occurs among Ediacaran organisms, leaves no clear signature in the fossil record. The apparent lack of sexual dimorphism and the simple, repetitive growth patterns displayed by many species suggest that these early complex organisms may have relied primarily on asexual reproduction methods that modern multicellular life has largely abandoned. This reproductive simplicity may explain both the success and ultimate evolutionary dead-end nature of many Ediacaran lineages. The chemical composition of Ediacaran organisms remains largely mysterious due to their lack of hard parts that might preserve original biochemical signatures. However, some studies suggest that these early complex life forms may have employed biochemical pathways that differ significantly from those used by modern animals. Alternative approaches to energy metabolism, different structural proteins, and novel mechanisms for cellular organization may have characterized these ancient organisms, representing biological solutions that evolution later discarded in favor of more efficient alternatives. Global climate during the Ediacaran period shows relative stability compared to the extreme conditions of earlier snowball Earth episodes, yet temperatures remain significantly warmer than modern conditions. Ice caps apparently exist at the poles, but tropical and temperate regions experience greenhouse conditions that allow complex life to flourish in shallow marine environments across much of the planet. These warm, stable conditions may provide the extended evolutionary time necessary for the development of large, complex body plans. The end of the Ediacaran period coincides with increasing atmospheric oxygen concentrations and the first appearance of small shelly fossils that herald the coming Cambrian explosion. Many classic Ediacaran organisms disappear from the fossil record before the Cambrian begins, suggesting that changing environmental conditions favored different approaches to multicellular organization. Whether these organisms went extinct or evolved into the more familiar animal forms of the Cambrian period remains one of paleontology's most intriguing unsolved questions. Ediacaran ecosystems demonstrate that large body size and complex organization can evolve through pathways completely different from those that characterize modern life. These ancient communities suggest alternative possibilities for multicellular organization that evolution explored briefly before settling on the more familiar patterns of animal and plant architecture that dominate later periods. The Ediacaran garden represents biological creativity unconstrained by the evolutionary precedents that will limit later innovations. And through these first experiments with complex multicellular life, Earth begins to explore the possibilities that will eventually lead to forests, coral reefs, and human civilizations. The Ediacaran organisms, strange as they appear to modern eyes, establish many fundamental principles of ecological organization, predator-prey relationships, habitat partitioning, ecosystem engineering that will persist throughout the remainder of life's history. The garden blooms in ancient seas, preparing the ground for all the biological complexity that follows. The soft bodies and quilted forms drift across Ediacaran sea floors with the patience of organisms that have no concept of the evolutionary revolutions waiting in their future. Each strange, beautiful creature represents millions of years of evolutionary experimentation, testing the possibilities of complex life in a world still innocent of the competitive pressures that will soon transform the nature of biological existence. The Cambrian explosion's patience unfolds across 25 million years of evolutionary experimentation, a span that seems instantaneous in geological terms, yet represents countless generations of biological innovation. Beginning roughly 540 million years ago, life suddenly discovers the architectural principles that will govern animal organization for the remainder of Earth's history. Eyes, shells, claws, and complex nervous systems appear in the fossil record with startling rapidity, as if evolution had been saving up innovations for hundreds of millions of years before releasing them all at once in a biological crescendo. Trilobites emerge as perhaps the most sophisticated early experiments in animal architecture, developing compound eyes that can detect polarized light and forming lenses from crystalline calcite with optical properties that human engineers have only recently learned to replicate. These marine arthropods explore nearly every conceivable ecological niche in Cambrian seas, from microscopic planktonic forms to massive predators over 2 feet in length. Their segmented bodies and jointed legs establish the basic arthropod body plan that will eventually give rise to insects, spiders, and crustaceans, making trilobites the ancestors of the most diverse animal group that has ever existed. The Burgess Shale preserves Cambrian life in extraordinary detail, capturing soft tissues and delicate structures that normally decay before fossilization can occur. Here, in deposits formed by underwater avalanches that buried entire communities instantly, paleontologists discover creatures so bizarre that they seem to represent entire phyla of animals that have no living relatives. Opabinia sports 5 mushroom-shaped eyes and a bizarre grasping claw at the end of a flexible proboscis. Wiwaxia bristles with defensive spines while crawling across the seafloor on rows of soft, slug-like feet. Anomalocaris, the Cambrian's first large predator, reaches lengths of over 6 feet and cruises through ancient seas propelled by undulating fins that run along its sides like living ribbons. Its circular mouth, lined with plates that close like a camera aperture, represents evolution's first serious attempt at large-scale predation in marine environments. This ancient monster establishes the ecological role of apex predator that will persist throughout the remainder of life's history, demonstrating that even the earliest complex ecosystems require multiple trophic levels to maintain stability. The mystery of the Cambrian explosion continues to puzzle evolutionary biologists who struggle to explain why complex animal body plans appear so suddenly in the fossil record. Some researchers propose that earlier, Precambrian animals possessed only soft parts that failed to fossilize, making their absence from older rocks an artifact of preservation rather than a true evolutionary pattern. Others suggest that the evolution of hard shells and skeletons during the early Cambrian creates a preservational bias that makes this period appear more innovative than it actually was. Atmospheric oxygen concentrations reach levels approaching modern values for the first time during the Cambrian period, providing the metabolic fuel necessary to support large, active organisms with complex internal organ systems. This oxygenation event enables the evolution of sophisticated circulatory systems, advanced nervous systems, and the energy-intensive process of shell formation that characterizes many Cambrian innovations. Higher oxygen levels also support increased metabolic rates that allow more rapid growth and more active lifestyles than earlier organisms could maintain. The development of predation during the Cambrian period triggers evolutionary arms races that accelerate the pace of morphological innovation. Prey species evolve shells, spines, and burrowing behaviors to avoid being eaten, while predators develop increasingly sophisticated methods for capturing and processing their food. These coevolutionary dynamics create positive feedback loops where innovation in one lineage drives counter-innovations in others, rapidly expanding the range of biological forms and functions present in Cambrian ecosystems. Cambrian seas teem with experimental approaches to multicellular organization, many of which prove evolutionary dead ends that leave no descendants in modern ecosystems. The five-eyed Opabinia represents an entire order of animals that vanished without trace. Hallucigenia, originally reconstructed upside down due to its bizarre anatomy, belongs to a group of spiny, walking organisms unlike anything alive today. These evolutionary experiments demonstrate that the Cambrian explosion involved extensive trial and error, with many innovative lineages failing to establish lasting success. The evolution of complex eyes occurs independently in multiple Cambrian lineages, suggesting that vision provides such significant survival advantages that evolution repeatedly discovers similar solutions to the challenge of detecting light and forming images. Trilobite compound eyes, mollusk camera eyes, and arthropod simple eyes all appear during this period, establishing the basic optical designs that will characterize animal vision throughout subsequent geological ages. The sudden appearance of sophisticated visual systems may itself help explain the Cambrian explosion, as predator-prey interactions become dominated by sight-based detection and avoidance. Bioturbation. The mixing of sediments by burrowing animals becomes extensive for the first time during the Cambrian period, fundamentally altering marine sedimentary environments. The three-dimensional exploration of seafloor sediments creates new ecological niches while destroying the laminated sedimentary structures that characterize Precambrian deposits. This biological modification of sedimentary environments represents one of the first examples of ecosystem engineering on a scale that affects global geological processes. Trace fossils become dramatically more diverse and complex during the Cambrian, recording sophisticated behavioral interactions between organisms and their environment. Elaborate burrow systems preserve evidence of complex feeding behaviors, while trackways record the movement patterns of early arthropods across ancient sea floors. Some trace fossils suggest primitive social behaviors, with multiple individuals following similar pathways or creating connected burrow systems that may indicate simple forms of cooperation or communication. The first mineralized skeletons appeared during the early Cambrian, as various animal lineages independently discover methods for precipitating calcium carbonate, calcium phosphate, and other minerals from seawater to create protective shells and supportive frameworks. These biomineralization processes require sophisticated cellular machinery for controlling crystal growth and incorporating organic matrices that give shells their strength and flexibility. The evolution of hard parts revolutionizes both ecology and preservation, creating the robust fossil record that allows detailed study of Cambrian life. Small shelly fossils that precede the main Cambrian explosion provide tantalizing glimpses of the evolutionary experimentation that led to fully formed animal body plans. These millimeter-sized shells, spines, and plates represent either juvenile stages of larger organisms or adult forms of entirely microscopic animals. Their simple, repetitive forms suggest intermediate stages between the soft-bodied Ediacaran organisms and the complex, mineralized animals of the later Cambrian. Ocean chemistry during the Cambrian period favors the precipitation of calcium carbonate shells and skeletons, providing the chemical conditions necessary for widespread biomineralization. Higher concentrations of dissolved calcium and carbonate ions in seawater make shell formation energetically feasible for the first time in Earth's history. These favorable chemical conditions may help explain why mineralized hard parts appear so suddenly in multiple, unrelated animal lineages during the early Cambrian. The Cambrian explosion establishes most of the major animal phyla that persist to the present day, creating the basic architectural templates for virtually all subsequent animal evolution. Arthropods, mollusks, echinoderms, chordates, and numerous other major groups make their first appearance during this remarkable period of biological innovation. Later evolution will elaborate on these Cambrian themes rather than discovering fundamentally new approaches to animal organization, suggesting that the basic constraints and possibilities of multicellular life become established during this ancient period, and through this explosion of biological creativity, Earth transforms from a world of simple, soft-bodied organisms to a planet where complex ecosystems support intricate food webs and sophisticated behavioral interactions. The Cambrian period establishes the fundamental ecological principles that will govern marine life for the next half-billion years, creating the foundation for all subsequent biological complexity while demonstrating evolution's extraordinary capacity for rapid innovation when environmental conditions become favorable for experimentation. Empty continents breathe under alien skies for hundreds of millions of years after the Cambrian explosion fills the oceans with complex life, their surfaces remaining as barren as the day they first emerged from primordial seas. No grass waves in ancient winds, no trees cast shadows across stone landscapes, no flowers bloom in valleys carved by rivers that flow through worlds of naked rock and sand. The land waits in silence, baked by a sun that shines through an atmosphere still learning the chemistry that will eventually support terrestrial ecosystems. Continental surfaces during the Ordovician and Silurian periods stretch endless and empty, broken only by the occasional green film of cyanobacteria coating rocks in permanently wet locations near rivers and lakes. These thin microbial mats represent the only life visible on vast landmasses that will someday support rainforests, grasslands, and human civilizations. The contrast between vibrant marine ecosystems teeming with trilobites, early fish, and diverse invertebrates, and the sterile continental interiors creates a planetary dichotomy that persists for nearly 200 million years. Weathering processes operate without biological interference during these early terrestrial ages, creating landscapes sculpted by purely physical and chemical forces. Mountains erode according to the mathematical laws of thermodynamics rather than the complex interactions between geology and biology that characterize modern terrestrial environments. Rivers carve channels through bedrock without the stabilizing influence of vegetation, creating braided networks that shift and meander with each flood season across broad, unvegetated floodplains. The absence of soil creates conditions unlike anything in the modern world, where biological processes have so thoroughly modified mineral weathering that true soil-free environments exist only in the most extreme locations. Early continental surfaces consist of fragmented rock, sand, and mineral precipitates arranged by wind and water into patterns that reflect purely geological processes. These pristine mineral environments preserve chemical signatures that will become obscured once life begins modifying continental weathering patterns. Atmospheric carbon dioxide concentrations remain dramatically higher than modern levels throughout this period of empty continents, creating greenhouse conditions that maintain warm temperatures even at high latitudes. Without terrestrial vegetation to remove carbon dioxide from the atmosphere through photosynthesis and soil formation, the carbon cycle operates through marine processes alone. Ocean-atmosphere carbon exchange provides the only biological feedback mechanism regulating global climate during these early terrestrial ages. The first tentative colonization of land begins not with plants, but with simple organisms that can survive periodic drying in the thin films of water that collect around rocks and in temporary pools. Cyanobacteria, the same organisms responsible for oxygenating Earth's atmosphere billions of years earlier, pioneer the transition from aquatic to terrestrial environments by developing protective sheaths and spore-like resting stages that can survive desiccation for extended periods. Primitive fungi emerge from marine environments during the late Ordovician period, establishing symbiotic relationships with early cyanobacteria and algae that allow both partners to survive the harsh conditions of terrestrial life. These early mycorrhizal associations represent evolution's first experiment with the cooperative relationships between different organisms that will prove essential for all subsequent terrestrial ecosystems. Fungal networks begin the slow process of breaking down rock surfaces and concentrating nutrients in ways that will eventually create soil. The mystery of life's transition from water to land involves solving numerous physiological challenges that marine organisms never face: desiccation, temperature fluctuations, ultraviolet radiation, and the absence of buoyant support, all present obstacles that require sophisticated adaptations before complex life can establish permanent residence on continental surfaces. Early terrestrial organisms must simultaneously evolve waterproof coverings, internal support structures, and mechanisms for gas exchange in air rather than water. Trace fossils preserve evidence of the earliest animal excursions onto land during the late Silurian period, recording brief forays by arthropods that venture onto shore to mate, molt, or escape predators before returning to aquatic environments. These trackways represent some of the earliest evidence of animal behavior on land, though they suggest temporary visits rather than permanent colonization. The footprints cross mudflats and sandy shores like ancient signatures of courage in an empty world. Simple plants finally begin their conquest of terrestrial environments during the late Silurian and early Devonian periods, initially as small, moss-like organisms that remain dependent on water for reproduction. These early land plants lack true roots, stems, or leaves, consisting instead of simple branching structures that absorb water and nutrients directly through their surfaces. Cooksonia and other primitive plants rarely exceed a few centimeters in height, creating the first terrestrial forests that barely rise above ankle level. The evolution of vascular tissue-specialized cells for transporting water and nutrients revolutionizes terrestrial plant architecture and allows the development of larger, more complex plant forms, xylem and phloem. The conducting tissues that transport fluids through plant bodies enable plants to grow taller and develop more sophisticated root systems that can extract water and minerals from deeper soil layers. These innovations establish the basic plant body plan that will support all future terrestrial vegetation. Soil formation accelerates dramatically once land plants establish permanent populations on continental surfaces. Plant roots and their associated fungal partners begin the chemical and physical breakdown of rock surfaces at rates far exceeding purely geological weathering processes. Dead plant material accumulates and decomposes, creating organic-rich layers that can retain moisture and nutrients. The first true soils represent a fundamentally new type of environment that exists nowhere else in the solar system. Early terrestrial ecosystems remain extremely simple compared to modern continental communities, consisting primarily of plants, fungi, bacteria, and primitive arthropods. Food webs contain only a few trophic levels, with herbivorous arthropods feeding on plant material and predatory arthropods feeding on the herbivores. The absence of vertebrates from early terrestrial communities creates ecological opportunities that will remain unexploited for millions of years after land plants establish extensive terrestrial vegetation. Continental drift during this period creates diverse climatic conditions across different land masses, allowing experimentation with terrestrial ecosystems under various environmental conditions. Some continents experience tropical conditions that favor rapid plant growth and extensive wetland development, while others endure more arid climates that select for drought-tolerant plant communities. These geographic variations in climate and terrain accelerate the diversification of early terrestrial life. The chemical composition of early terrestrial atmospheres differs significantly from modern conditions, with higher carbon dioxide concentrations and lower oxygen levels affecting plant physiology and growth patterns. Early land plants develop under atmospheric conditions that would stress or kill many modern plant species, suggesting that initial terrestrial vegetation employed biochemical pathways that have since been modified or abandoned as atmospheric composition changed. Rivers and streams begin to interact with terrestrial vegetation for the first time during this period, creating feedback loops between biological and geological processes that will characterize all future terrestrial environments. Plant roots stabilize riverbanks and reduce erosion, while plant debris creates logjams and modifies flow patterns. These biological modifications of hydrological processes begin the transformation of purely geological landscapes into the integrated Earth system where biology and geology operate as coupled processes. And through these first tentative steps toward terrestrial life, Earth begins the transformation that will eventually create the continental ecosystems capable of supporting complex terrestrial food webs, including the mammals that will give rise to human civilization. The empty continents slowly learn to breathe with the rhythm of photosynthetic life, exhaling oxygen and inhaling carbon dioxide in the planetary respiration that will regulate global climate for the remainder of Earth's history. The silence of barren continents gradually fills with the whisper of wind through primitive vegetation and the subtle sounds of arthropods exploring this new terrestrial frontier. The land prepares for the forests, grasslands, and complex terrestrial communities that will follow, establishing the basic biological and geochemical processes that make continental life possible. Plants pioneer the impossible transition from aquatic to terrestrial life during the Devonian period, transforming empty continents into landscapes that begin to resemble recognizable ecosystems for the first time in Earth's history. These botanical explorers solve fundamental engineering problems that no organism has ever faced: how to stand upright without water's buoyant support, how to transport fluids through tall structures, how to reproduce without swimming sperm, creating solutions that will support all future terrestrial life. The first forests rise from swampy lowlands during the Middle Devonian. Though these ancient woodlands bear little resemblance to modern temperate or tropical forests, Archaeopteris, among the earliest true trees, reaches heights of over 100 feet while developing the first sophisticated root systems capable of anchoring large plants in terrestrial substrates. These primitive giants possess fern-like leaves but reproduce through spores rather than seeds, creating forests that combine familiar and alien characteristics in ways that challenge modern botanical understanding. Vascular tissue architecture becomes increasingly sophisticated as plants experiment with different approaches to long-distance transport of water and nutrients. Early wood develops as plants learn to deposit lignin, a complex polymer that provides structural support in cell walls, creating the rigid internal skeletons that allow terrestrial plants to achieve large size. The evolution of wood represents one of biology's most significant innovations, providing not only structural support but also efficient pathways for fluid transport and storage reservoirs for carbon that will influence global climate for millions of years. Seed plants emerged during the late Devonian period, developing reproductive strategies that finally free terrestrial vegetation from dependence on water for sexual reproduction. Seeds represent sophisticated survival capsules that can remain dormant for extended periods before germinating under favorable conditions, allowing plants to colonize habitats far from permanent water sources. This reproductive innovation proves so successful that seed plants will eventually dominate most terrestrial ecosystems, relegating spore-bearing plants to specialized ecological niches. Root systems become increasingly elaborate as plants compete for water and nutrients in terrestrial substrates, developing extensive underground networks that can penetrate deeply into soil layers and spread laterally across wide areas. These root systems establish symbiotic relationships with fungi that extend their effective reach even further, creating underground trading networks where plants exchange carbon compounds for essential minerals. The evolution of sophisticated root architecture fundamentally alters terrestrial geochemistry by accelerating rock weathering and soil formation. Leaves undergo rapid diversification during the Devonian period as plants experiment with different approaches to capturing sunlight and regulating gas exchange. Early leaves remain small and simple to minimize water loss, but increasing atmospheric humidity and more sophisticated water transport systems allow the development of larger, more complex leaf forms. The variety of leaf shapes and sizes in Devonian forests suggests intense experimentation with photosynthetic efficiency under different environmental conditions. Photosynthetic biochemistry becomes more efficient as land plants adapt to terrestrial light conditions that differ significantly from the filtered illumination available in aquatic environments. C3 photosynthesis. The metabolic pathway used by most modern plants reaches high efficiency during this period as plants develop sophisticated mechanisms for concentrating carbon dioxide and minimizing photorespiration. These biochemical improvements allow terrestrial plants to achieve growth rates that quickly outpace their aquatic ancestors. The first plant-animal interactions on land develop as arthropods discover terrestrial vegetation as both habitat and food source, establishing ecological relationships that will persist throughout the remainder of terrestrial evolution. Early herbivorous insects begin the co-evolutionary arms race between plants and plant eaters that drives much subsequent evolutionary innovation in both groups. Plants develop chemical defenses, physical barriers, and induced responses to herbivory, while insects evolve increasingly sophisticated methods for overcoming plant defenses. Terrestrial carbon storage increases dramatically as plants begin accumulating large amounts of organic matter in wood, roots, and soil organic matter. This biological carbon sequestration begins to influence global climate by removing carbon dioxide from the atmosphere at rates that exceed the release of carbon through volcanic outgassing and rock weathering. The first forests established the crucial role of terrestrial vegetation in regulating planetary climate that will characterize all subsequent geological periods. Soil ecosystems become increasingly complex as decomposer organisms learn to break down the lignin and cellulose that comprise woody plant material. Bacteria and fungi develop specialized enzymes for digesting these complex organic polymers, establishing the biochemical recycling processes that allow nutrients to cycle between living plants and soil organic matter. Early soil food webs remain simple, but establish the fundamental ecological principles that govern all subsequent terrestrial nutrient cycling. The mystery of plant colonization strategies during this period reveals sophisticated approaches to landscape-scale ecosystem establishment that suggest remarkable coordination among different plant species. Fossil evidence indicates that early forests often establish themselves through predictable successional sequences where pioneer species modify soil conditions to favor later arriving species that eventually replace them. These succession patterns suggest that even early terrestrial plants possessed ecological strategies for ecosystem development that resemble modern forest dynamics. Atmospheric composition begins to shift as terrestrial photosynthesis removes increasing amounts of carbon dioxide from the atmosphere while releasing oxygen at rates that supplement marine photosynthetic production. This terrestrial contribution to atmospheric oxygenation creates more favorable conditions for animal respiration and may help explain the subsequent colonization of land by vertebrates during the late Devonian period. Plants begin their role as planetary atmospheric regulators that will persist throughout subsequent Earth history. Water cycling between terrestrial and atmospheric reservoirs becomes more complex as plant transpiration adds a biological component to the hydrological cycle that operates independently of purely physical evaporation processes. Plant-controlled water transport from soil to atmosphere creates more complex patterns of atmospheric humidity and precipitation that begin to influence regional climate patterns. The establishment of plant-mediated water cycling represents another crucial step in the development of the integrated Earth system. Wetland ecosystems proliferate during the Devonian period as plants adapt to permanently saturated soils that create unique chemical and physical conditions for root growth and organic matter accumulation. These early wetlands become centers of rapid plant evolution and high biological productivity, while also serving as major sites of carbon storage that will eventually form coal deposits. Wetland plants develop specialized adaptations for life in waterlogged soils, including air-conducting tissues and alternative metabolic pathways for anaerobic conditions. The first plant communities begin to modify local climates through their effects on surface albedo, evapotranspiration, and wind patterns, creating feedback loops between vegetation and atmospheric conditions that establish the foundation for complex climate-vegetation interactions. Dark forest canopies absorb more solar radiation than bare rock or soil surfaces, while plant transpiration increases local humidity and can trigger precipitation. These biological climate feedbacks begin the tight coupling between terrestrial ecosystems and atmospheric processes that characterizes modern Earth, and through these botanical innovations, Earth undergoes perhaps the most dramatic transformation in its surface environments since the origin of oxygenic photosynthesis billions of years earlier. The colonization of land by plants creates entirely new types of ecosystems while fundamentally altering global biogeochemical cycles and climate regulation. Continents transition from sterile mineral surfaces to biologically active landscapes capable of supporting the complex terrestrial food webs that will eventually include dinosaurs, mammals, and human civilizations. The patience of plant pioneers paying off across millions of years of experimentation, establishing the terrestrial foundation for all subsequent continental life while demonstrating evolution's remarkable ability to solve fundamental engineering challenges through biological innovation. The impossible becomes inevitable as plants transform the very nature of terrestrial environments and prepare the stage for the colonization of land by animals. Insects inherit silence and transform it into the first complex terrestrial societies, establishing dominion over land environments millions of years before vertebrates venture beyond the water's edge. These six-legged pioneers develop sophisticated social structures, communication systems, and ecological relationships that demonstrate intelligence and coordination rivaling any future terrestrial organisms. The arthropod conquest of land proceeds with methodical thoroughness, creating intricate societies that will persist largely unchanged for hundreds of millions of years. The first insects emerge from aquatic ancestors during the late Silurian and early Devonian periods. Initially, as wingless creatures that scuttle through primitive plant communities like terrestrial versions of their marine arthropod relatives, these early insects possess the basic hexapod body plan, 3 body segments, 6 legs, and compound eyes that will prove so successful that it remains virtually unchanged throughout subsequent evolutionary time. The fundamental insect architecture appears almost perfectly suited for terrestrial life from its very first appearance. Wings develop independently in insects during the Carboniferous period, creating the first powered flight in Earth's history and opening 3-dimensional aerial habitats that no other organisms can exploit. Early insect wings may have evolved from gill plates used for gas exchange in aquatic environments, repurposed for aerial locomotion as insects adapted to terrestrial life. The evolution of flight transforms insect ecology by allowing rapid dispersal, escape from ground-based predators, and access to aerial food sources unavailable to other terrestrial organisms. Dragonflies reach enormous sizes during the Carboniferous period, with some species achieving wingspans of over 2 feet as they cruise through ancient forests in pursuit of smaller flying insects. These giant predators benefit from atmospheric oxygen concentrations that reach 35%, nearly double modern levels, which allows the passive respiratory systems of insects to support much larger body sizes than current atmospheric chemistry permits. Meganeura, the largest known insect, represents the peak of arthropod gigantism made possible by the unique atmospheric conditions of the late Paleozoic era. Social behavior emerges early in insect evolution, with primitive termites developing complex colony structures that allow efficient exploitation of dead plant material in early terrestrial ecosystems. These ancient social insects construct elaborate nests, maintain sophisticated communication systems through chemical signals, and divide labor among specialized castes in ways that foreshadow the advanced eusocial systems of modern ants, bees, and termites. Insect societies achieve levels of organization and coordination that will not appear in vertebrate societies for hundreds of millions of years. The mystery of insect success lies partly in their remarkable diversity of feeding strategies that allow exploitation of virtually every terrestrial food source. Early insects develop mouthparts adapted for chewing plant material, piercing and sucking plant fluids, predation on other arthropods, and decomposition of dead organic matter. This feeding versatility allows insects to occupy ecological niches at every trophic level in terrestrial food webs, establishing their dominance over terrestrial arthropod communities that persists to the present day. Metamorphosis evolves as insects develop increasingly sophisticated life cycles that allow different developmental stages to exploit different ecological niches without competition between juveniles and adults. Complete metamorphosis, where larvae undergo dramatic transformation into morphologically distinct adults, represents one of evolution's most complex developmental innovations. This life cycle strategy allows single species to occupy multiple ecological roles simultaneously, dramatically increasing their ecological impact and evolutionary success. Insect respiratory systems demonstrate elegant solutions to the challenges of gas exchange in terrestrial environments, developing tracheal networks that deliver oxygen directly to internal tissues without requiring circulatory systems for oxygen transport. These air-filled tubes penetrate throughout insect bodies, creating efficient respiratory systems that function effectively at small body sizes but become limiting factors for gigantism under normal atmospheric oxygen concentrations. The tracheal system represents a fundamentally different approach to respiratory physiology than the lung-based systems that vertebrates will later develop. Chemical communication reaches extraordinary sophistication in early insect societies as these organisms develop complex pheromone systems for coordinating group behavior, marking territories, and facilitating mating. Insect chemical signals can convey detailed information about food sources, danger levels, reproductive status, and individual identity through molecular messages that operate with precision, rivaling any subsequent communication system. These chemical languages allow insects to coordinate complex social behaviors without requiring the large brains that vertebrate societies will eventually develop. Pollination relationships between insects and plants begin during the Carboniferous period as both groups discover mutual benefits from cooperative interactions. Early beetles and primitive flies feed on plant reproductive structures while inadvertently transferring pollen between flowers, establishing co-evolutionary relationships that will drive much subsequent diversification in both insects and flowering plants. These pollination mutualisms represent some of evolution's first examples of sophisticated interspecific cooperation that benefits both partners. Insect defense mechanisms become increasingly elaborate as predation pressure from spiders, early vertebrates, and other insects drives the evolution of sophisticated anti-predator adaptations. Camouflage, chemical defenses, mimicry, and warning coloration all appear in early insect lineages, demonstrating that even ancient terrestrial ecosystems supported complex predator-prey interactions that selected for increasingly sophisticated survival strategies. Some carboniferous insects develop defensive chemicals so potent that their molecular signatures persist in fossil deposits hundreds of millions of years later. The ecological impact of insects on early terrestrial ecosystems proves enormous despite their small individual size. As these organisms begin to influence plant reproduction, soil formation, decomposition rates, and nutrient cycling in ways that shape entire ecosystem structure and function. Insect herbivory drives plant evolution toward increasingly sophisticated defensive strategies, while insect decomposer activity accelerates organic matter breakdown and nutrient recycling. Early terrestrial ecosystems become dominated by insect-mediated ecological processes that will persist throughout subsequent evolutionary time. Engineering sophistication in insect construction projects rivals any subsequent biological architecture as social species develop increasingly complex nest structures, galleries, and defensive installations. Early termites construct elaborate underground cities with sophisticated ventilation systems, fungus gardens, and defensive chambers that demonstrate remarkable understanding of architectural principles. These insect engineering projects represent some of the earliest examples of ecosystem modification by terrestrial organisms. Navigation abilities in flying insects reach extraordinary sophistication as these organisms develop multiple sensory systems for orientation during flight, including visual landmark recognition, polarized light detection, and magnetic field sensitivity. Early flying insects must solve complex three-dimensional navigation problems in environments where wind patterns, terrain features, and atmospheric conditions create challenging flight conditions. The neurological mechanisms underlying insect navigation represent sophisticated computational systems operating in remarkably small brains. Overwintering strategies develop as insects adapt to seasonal climate variations in terrestrial environments that lack the thermal stability of aquatic habitats. Diapause, the insect equivalent of hibernation, allows survival through unfavorable seasons by reducing metabolic rates and entering dormant states that can persist for months. These physiological adaptations to terrestrial seasonality represent crucial innovations that allow insect survival in temperate and polar climates that would otherwise prove uninhabitable. And through these arthropod innovations, terrestrial ecosystems achieve levels of complexity and sophistication that will provide the ecological foundation for all subsequent terrestrial life. Insects establish the basic principles of terrestrial food, web organization, interspecific cooperation, chemical communication, and ecosystem engineering that will characterize continental ecosystems throughout the remainder of Earth's history. The six-legged inheritors of silent continents transform terrestrial environments into vibrant, complex ecological systems that demonstrate remarkable biological sophistication, operating on scales from individual organisms to entire landscapes. The buzz and hum of insect activity begins to fill terrestrial soundscapes as these pioneers establish the acoustic signatures of complex ecosystem function. The silence inherited from empty continents gives way to the subtle but persistent sounds of biological activity that indicate healthy, functioning terrestrial communities capable of supporting increasingly complex forms of life. Forests before decay create landscapes unlike anything in the modern world, where vast accumulations of dead wood pile higher each year because fungi have not yet learned the biochemical keys to unlock lignin's complex molecular structure. During the Carboniferous period, trees grow, die, and fall into swampy lowlands where they resist decomposition for millions of years, creating organic deposits hundreds of feet thick that will eventually transform into the coal seams that power human industrial civilization 300 million years later. Lepidodendron and Sigillaria, the giant club mosses and horsetails of Carboniferous forests, reach heights of over 130 feet while developing internal support structures fundamentally different from modern trees. These ancient giants grow from their tips rather than developing woody trunks, creating hollow cylindrical stems supported by thick bark that can comprise 90% of the tree's diameter. When these peculiar trees die and fall, their unique anatomy creates logs that resist bacterial decay while their hollow interiors fill with sediment, preserving detailed fossil evidence of forest structure in ways that modern woody trees never could. The absence of white rot fungi during most of the Carboniferous period creates a critical gap in forest ecosystem function that allows organic matter to accumulate at rates far exceeding decomposition. Lignin, the complex polymer that gives wood its strength and rigidity, proves biochemically impervious to the decomposer organisms available during this ancient period. Dead trees pile up in swampy forests like biological lumberyards, with each fallen log adding to accumulations that grow thicker and more extensive with each passing millennium. Atmospheric oxygen concentrations reach their highest levels in Earth's history during the Carboniferous period, approaching 35% as massive amounts of organic carbon become buried in swamp deposits rather than being decomposed and return to the atmosphere as carbon dioxide. This oxygen spike creates atmospheric conditions that support giant insects while simultaneously making wildfires burn with unprecedented intensity. Lightning strikes in these oxygen-rich forests create conflagrations that can consume vast areas of accumulated deadwood in fires that burn hotter and faster than anything in the modern world. A coal formation begins as buried plant material undergoes gradual chemical transformation under the pressure and heat of accumulating sediments. Peat deposits, formed from partially decomposed plant material in waterlogged conditions, slowly transform into lignite, then bituminous coal, and finally anthracite through geological processes that require millions of years to complete. Each ton of coal represents the compressed remains of approximately 10 tons of original plant material, making coal deposits vast repositories of ancient solar energy captured by Carboniferous photosynthesis. The mystery of lignin's initial resistance to biological breakdown suggests that this complex organic polymer evolved as an anti-herbivore defense rather than as structural support, with its resistance to decomposition being an unintended consequence rather than an adaptive function. Lignin's molecular structure incorporates random cross-linking patterns that make it extremely difficult for enzymes to attack systematically, creating a biochemical puzzle that early decomposer organisms cannot solve. This accidental resistance to decay fundamentally alters global carbon cycling for millions of years. Swamp ecosystems during the Carboniferous period develop unique characteristics that have no modern analogues, supporting diverse communities of plants and animals in environments where standing water, high humidity, and accumulated organic matter create chemical conditions favorable for fossil preservation. These ancient wetlands maintain consistently high water tables that prevent oxidative decomposition while providing the anaerobic conditions necessary for peat formation. The chemistry of Carboniferous swamps resembles a planetary-scale pickle barrel that preserves organic matter through acidic, oxygen-free conditions. Early fungi possess decomposer capabilities limited to relatively simple organic compounds like cellulose and simple carbohydrates, lacking the sophisticated enzyme systems necessary to break down lignin's complex three-dimensional structure. Brown rot fungi, which can decompose cellulose while leaving lignin relatively intact, dominate early forest decomposer communities and contribute to the selective preservation of woody tissues in swamp deposits. The evolution of white rot fungi, capable of completely breaking down lignin, represents a crucial biochemical innovation that will fundamentally alter forest ecosystem function. Seed ferns and early conifers begin to dominate Carboniferous forests, as these groups develop reproductive strategies better adapted to the fluctuating water levels and seasonal climate variations that characterize this period. These plants invest heavily in lignin-rich support tissues that provide structural integrity while creating the vast organic carbon reservoirs that accumulate in swamp deposits. The success of lignin-producing plants during this period inadvertently creates the geological foundations for future human industrial activity. Continental drift during the Carboniferous period creates extensive tropical swamplands across equatorial regions where warm, humid conditions favor rapid plant growth and organic matter accumulation. The collision of continental masses creates broad, low-lying basins that fill with shallow water and support vast wetland ecosystems stretching across thousands of square miles. These geological conditions prove ideal for coal formation, concentrating organic matter accumulation in specific geographic regions that will later become major coal-producing areas. Arthropod communities in Carboniferous forests develop remarkable diversity as insects, spiders, and other terrestrial arthropods exploit the abundant plant resources and complex three-dimensional habitat structure provided by tall forests. Giant millipedes reach lengths of over 6 feet as they feed on decaying plant material, while enormous dragonflies patrol forest clearings in pursuit of smaller flying insects. The high oxygen concentrations support arthropod gigantism that creates forest communities dominated by creatures that would seem fantastical by modern standards. River systems flowing through carboniferous swamplands transport enormous quantities of organic debris from upstream forests, creating downstream deposits where plant material accumulates in point bars, oxbow lakes, and floodplain wetlands. These fluvial transport processes distribute organic matter across broad geographic areas, creating the extensive coal seam networks that characterize many carboniferous geological formations. The interaction between forest productivity, river transport, and swamp deposition creates ideal conditions for large-scale coal formation. Climate during the Carboniferous period fluctuates between greenhouse and icehouse conditions, as the massive burial of organic carbon removes carbon dioxide from the atmosphere while increasing oxygen concentrations. These atmospheric changes create feedback loops that influence global temperature, precipitation patterns, and ice sheet formation in ways that have no modern analog. The unique atmospheric composition of the Carboniferous period supports ecosystem processes that operate according to different rules than modern biogeochemical cycles. Marine ecosystems during this period experience the consequences of terrestrial organic matter burial as reduced atmospheric carbon dioxide levels affect ocean chemistry and global climate patterns. The massive carbon storage in terrestrial swamps influences marine productivity, ocean circulation, and the distribution of marine organisms in ways that demonstrate the global interconnectedness of Earth's biogeochemical systems. Terrestrial coal formation becomes a planetary-scale geological process that affects every major Earth system. The eventual evolution of lignin-degrading enzymes by white rot fungi represents one of evolution's most consequential biochemical innovations, finally closing the decomposition loop that allows efficient recycling of organic matter in forest ecosystems. When fungi finally crack linin's molecular code, forest ecosystem function changes dramatically as dead wood begins decomposing rapidly rather than accumulating indefinitely. This biochemical breakthrough effectively ends the Carboniferous period's unique conditions for massive coal formation. And through these extraordinary forest ecosystems, Earth conducts its largest experiment in carbon storage, sequestering vast amounts of atmospheric carbon in geological deposits that will remain buried for hundreds of millions of years. The forests before decay create the energy resources that will eventually power human civilization, while demonstrating how evolutionary innovations can have consequences that extend far beyond their immediate biological context. The accumulation continues with geological patience, each fallen tree adding to deposits that grow imperceptibly thicker with each passing year. The swamps exhale methane and hydrogen sulfide while inhaling the remains of ancient forests, creating the underground energy banks that will fuel technology and industry in an unimaginably distant future when hairless apes learn to dig coal from the ground. The Great Dying's reset begins not with visible catastrophe, but with subtle changes in ocean chemistry that unfold across thousands of years, like a slow-motion apocalypse at the end of the Permian period. Volcanic activity in Siberia releases unprecedented volumes of lava, ash, and toxic gases into the atmosphere, while deep ocean waters become increasingly acidic and oxygen-depleted. The largest mass extinction in Earth's history eliminates over 90% of marine species and 70% of terrestrial vertebrates. Yet it proceeds with the patience of geological processes operating on timescales that make human catastrophes seem instantaneous. The Siberian traps. one of the largest volcanic events in Earth's history, pump millions of cubic kilometers of basaltic lava across an area larger than Western Europe while simultaneously releasing vast quantities of carbon dioxide, sulfur dioxide, and other greenhouse gases into the atmosphere. This volcanic paroxysm continues for nearly 2 million years, creating a sustained environmental perturbation that overwhelms the Earth system's normal capacity for self-regulation. The sheer scale of volcanic activity during this period has no equivalent in more recent geological time, representing a planetary-scale industrial accident powered by internal geological forces. Ocean acidification during the end. Permian extinction reaches levels that dissolve calcium carbonate shells and skeletons faster than marine organisms can build them, creating marine environments where shell-bearing creatures face biochemical impossibility. The chemistry of seawater shifts so dramatically that organisms with carbonate hardparts, trilobites, corals. Many mollusks find their basic survival strategies rendered obsolete by changing environmental conditions. Ancient reef ecosystems collapse as the fundamental chemistry that supports their existence disappears from ocean water. Hydrogen sulfide poisoning transforms ocean basins into toxic environments as anaerobic bacteria proliferate in oxygen-depleted deep waters, producing deadly gases that eventually reach surface waters and escape into the atmosphere. Purple and green sulfur bacteria, which thrive in environments lethal to most other organisms, begin to dominate marine ecosystems as normal photosynthetic plankton succumb to acidic, toxic conditions. The oceans literally turn purple as bacterial communities adapted to extreme conditions replace the diverse marine ecosystems that had flourished for millions of years. Atmospheric temperatures rise by perhaps 8 to 10 degrees Celsius above pre-extinction levels as greenhouse gas concentrations reach extremes not seen since Earth's earliest geological periods. This global warming creates tropical conditions extending to polar regions, while simultaneously triggering more intense weather patterns and seasonal extremes. The thermal stress alone proves lethal to many organisms, while changes in precipitation patterns disrupt terrestrial ecosystems that had adapted to more stable climate conditions. The collapse of terrestrial ecosystems follows a cascade pattern where the extinction of key species triggers secondary extinctions throughout interconnected food webs. Large herbivorous vertebrates disappear first, followed by the carnivores that depend on them. Then the smaller organisms that relied on the ecosystem engineering activities of larger species. Plant communities suffer massive extinctions as pollinators vanish and soil ecosystems collapse under the stress of climate change and acid precipitation. Marine food webs simplify dramatically as complex ecosystems with multiple trophic levels collapse into simple communities dominated by a few stress-tolerant species. The rich diversity of Paleozoic marine life trilobites, rugose corals, blastoid echinoderms, and countless other lineages vanishes almost entirely, leaving ocean ecosystems impoverished in ways that will require millions of years to repair. The few surviving marine organisms represent evolutionary refugees from more complex ecosystems that no longer exist. The mystery of recovery patterns following the Great Dying reveals that ecosystem restoration proceeds much more slowly than ecosystem collapse, requiring nearly 10 million years for marine diversity to approach pre-extinction levels. Early Triassic ecosystems remain remarkably simple and unstable, with frequent local extinctions and recolonizations suggesting that environmental conditions remain too harsh for complex community development. The planet appears to require extensive time to re-establish the stable environmental conditions necessary for diverse ecosystems. Stromatolites make a temporary comeback during the early Triassic period as bacterial communities reclaim ecological niches left vacant by the extinction of more complex organisms. These microbial mats, which had been largely displaced by animal communities hundreds of millions of years earlier, briefly dominate shallow marine environments as ecosystem succession essentially restarts from its most primitive phases. The return of stromatolites demonstrates how severe environmental stress can reset ecosystem development to much earlier evolutionary stages. Soil ecosystems collapse across much of the terrestrial realm as plant extinctions eliminate the primary producers that support complex soil food webs. Erosion rates increase dramatically as vegetation cover disappears and root systems that normally stabilize soil structure decay away. Rivers carry enormous sediment loads across barren landscapes, depositing thick layers of sterile sand and silt in downstream basins where diverse wetland ecosystems had previously flourished. Fungal communities apparently expand their ecological role during the extinction crisis, as vast quantities of dead plant and animal material provide abundant food resources for decomposer organisms. Some researchers suggest that fungal spores dominate sedimentary deposits from the extinction boundary, indicating that saprophytic fungi briefly became the most abundant organisms in many terrestrial environments. This fungal spike suggests that decomposition processes temporarily overwhelm primary production as ecosystems collapse. The carbon isotope signature of the end Permian extinction preserves evidence of massive disruptions to the global carbon cycle as both marine and terrestrial carbon reservoirs experience unprecedented perturbations. Organic carbon burial rates plummet as marine productivity collapses, while carbon dioxide emissions from volcanic activity and organic matter decomposition overwhelm the Earth system's normal carbon sinks. The isotopic evidence suggests that global carbon cycling essentially breaks down for several million years. Evolutionary innovation accelerates paradoxically during and after the extinction crisis as surviving lineages undergo rapid adaptive radiation to fill empty ecological niches. Archosaurs, the group that will eventually give rise to dinosaurs and crocodiles, begin their diversification during the early Triassic period. Similarly, the ancestors of mammals and modern amphibians trace their early evolution to post-extinction adaptive radiations that occurred as survivors exploited vacant ecological opportunities. The selective patterns of extinction and survival during the Great Dying reveal that environmental tolerance and physiological flexibility prove more important for survival than size, complexity, or previous evolutionary success. Small, generalist organisms with broad environmental tolerances survive at higher rates than large, specialized species that require specific environmental conditions. This selection for generalists temporarily reverses the evolutionary trend toward increasing specialization that had characterized late Paleozoic ecosystems. Recovery ecosystems demonstrate remarkable convergence as different lineages independently evolve similar solutions to survival in post-extinction environments. Early Triassic marine communities show repeated evolution of small body size, simple morphology, and broad environmental tolerance among survivors, suggesting that harsh environmental conditions impose strong selection for similar adaptive strategies across taxonomically diverse groups. And through this greatest of all biological catastrophes, Earth demonstrates both the fragility and resilience of complex life while establishing the principle that mass extinctions, despite their destructive impact, also create opportunities for evolutionary innovation. The Great Dying clears ecological space for entirely new types of organisms and ecosystems, setting the stage for the Mesozoic era's experiments with dinosaurian gigantism and the eventual rise of flowering plants and modern ecosystem structures. The reset continues for millions of years as Earth slowly rebuilds its biological complexity from the few hardy survivors of the greatest catastrophe in the history of complex life. Each extinct lineage represents millions of years of evolutionary experimentation lost forever. Yet each surviving lineage carries the potential for new innovations that will reshape the nature of life on Earth. Dinosaurs' long democracy begins in the aftermath of the Great Dying's ecological chaos, as Archosaur survivors spread across empty landscapes and evolve into the most successful large vertebrates in Earth's history. For 165 million years, a span 3 times longer than mammals have dominated terrestrial ecosystems. Dinosaurs rule continental environments while experimenting with body sizes, social behaviors, and ecological strategies that explore the outer limits of vertebrate possibility. Yet, throughout this vast temporal reign, dinosaurian intelligence remains constrained within patterns that never approach the technological sophistication that will eventually characterize human civilization. The first dinosaurs emerged during the late Triassic period as small, bipedal predators little larger than modern house cats, their modest proportions offering no hint of the giants they will eventually become. Eoraptor and Herrerasaurus scurry through early Mesozoic forests, establishing the basic dinosaurian body plan upright stance, hollow bones, efficient metabolism that will prove so successful that it persists essentially unchanged throughout the group's long evolutionary experiment. These early forms demonstrate that even the most successful evolutionary innovations often begin with humble, unassuming ancestors. Sauropod gigantism reaches unprecedented extremes during the Jurassic period as Brachiosaurus, Diplodocus, and their relatives achieve body masses approaching 80 tons while developing feeding strategies that allow them to process enormous quantities of low-quality plant material. These living skyscrapers engineer their own gravitational challenges, developing hearts powerful enough to pump blood up necks stretching 30 feet or more while maintaining blood pressure sufficient to supply oxygen to brains positioned far above their cardiovascular systems. The physics of sauropod circulation requires biological solutions to engineering problems that no other land animals ever face. Theropod diversity explodes across ecological niches, from tiny feathered insectivores to massive apex predators like Tyrannosaurus rex, demonstrating the remarkable evolutionary plasticity of the basic dinosaurian Bayou plan. Compsognathus pursues prey no larger than modern lizards through Jurassic undergrowth, while Giganotosaurus develops hunting strategies for taking down sauropods weighing more than 10 elephants. The range of body sizes within theropod dinosaurs spans nearly 4 orders of magnitude, creating ecological opportunities for dinosaurian predators at every scale from insect hunting to megafauna predation. Social behaviors in dinosaurs reach sophisticated levels that rival those of modern large mammals, with evidence for complex group dynamics, parental care, and cooperative hunting strategies preserved in trackway sites and nesting colonies across multiple continents. Maiasaura colonies contain hundreds of nests arranged in organized patterns that suggest community-level coordination in nest site selection and colony defense. Some theropod trackways preserve evidence of coordinated pack hunting by multiple individuals pursuing large prey animals across ancient landscapes. The mystery of dinosaurian intelligence remains tantalizingly incomplete despite decades of research into brain structure, behavior, and ecological complexity. While some theropods develop brain-to-body ratios approaching those of modern birds, their direct descendants and demonstrate sophisticated behaviors, including tool use and complex social coordination. No dinosaurian lineage evolves the combination of manual dexterity, vocal communication, and technological innovation that characterizes human intelligence. The constraints that prevent dinosaurian evolution toward technological civilization remain unclear, but apparently prove insurmountable throughout their 165 million year tenure. Feathered dinosaurs emerged during the Jurassic period. Initially, as simple filamentous structures for insulation, that gradually evolve into the complex flight feathers that will eventually allow some lineages to exploit aerial environments. Sinosauropteryx displays primitive feathers resembling modern down, while Microraptor develops four-winged flight capabilities that represent an evolutionary experiment with powered flight that differs dramatically from the two-winged flight plan that modern birds eventually perfect. These feathered forms demonstrate that the avian body plan emerges gradually from theropod dinosaur lineages through incremental innovations rather than sudden evolutionary leaps. Herbivorous dinosaurs develop increasingly sophisticated approaches to processing plant material as flowering plants begin to diversify during the Cretaceous period, creating new coevolutionary relationships between dinosaurian herbivores and angiosperm vegetation. Hadrosaurs evolve complex dental batteries containing hundreds of individual teeth for grinding tough plant fibers, while ceratopsians develop massive jaw muscles and beak-like structures for processing fibrous vegetation. These feeding innovations drive plant evolution toward chemical defenses and structural modifications that influence the diversification of flowering plant communities. Climate during the Mesozoic era remains consistently warmer than modern conditions, with no polar ice caps and tropical conditions extending to high latitudes, creating environmental stability that allows dinosaurian ecosystems to persist with relatively minor modifications for over 100 million years. This climatic stability contrasts sharply with the dramatic climate fluctuations that characterize more recent geological periods and may contribute to the evolutionary conservatism that keeps dinosaurian lineages within similar ecological roles for extraordinarily long periods. Marine reptiles during the dinosaur era developed gigantism and ecological specializations that parallel dinosaurian terrestrial innovations while remaining completely separate evolutionary lineages. Plesiosaurs evolve feeding strategies for exploiting marine food webs, while ichthyosaurs converge on dolphin-like body forms for high-speed aquatic pursuit predation. Mosasaurs eventually reach lengths exceeding 50 feet as they dominate late Cretaceous marine ecosystems, demonstrating that reptilian success during the Mesozoic extends far beyond terrestrial dinosaurs. Flowering plants undergo explosive diversification during the Cretaceous period, fundamentally altering terrestrial ecosystems while creating new ecological opportunities and constraints for dinosaurian herbivores. The evolution of grasses, fruits, and complex chemical defense systems in angiosperms drives corresponding innovations in dinosaurian feeding strategies, tooth morphology, and digestive physiology. This plant-animal coevolution creates increasingly complex terrestrial ecosystems while maintaining the basic ecological structure that keeps dinosaurs in dominant roles. Atmospheric composition during the Mesozoic era differs significantly from modern conditions, with higher carbon dioxide concentrations and somewhat lower oxygen levels, creating physiological challenges and opportunities that shape dinosaurian evolution in ways that have no modern analogues. The enhanced greenhouse effect maintains global temperatures that support reptilian metabolism at high latitudes, while atmospheric composition favors certain types of plant communities that influence herbivorous dinosaur evolution. Geographic isolation during the Mesozoic era drives dinosaurian evolution along different trajectories on different continents, as Pangaea breaks apart and continental drift creates isolated landmasses with distinct evolutionary histories. South American titanosaurs evolve along different lines than Asian sauropods, while North American and European theropod communities develop distinct ecological characteristics. This geographic diversification creates dinosaurian endemism that demonstrates evolution's capacity for independent innovation under similar environmental conditions. Dinosaurian reproduction involves sophisticated behaviors, including elaborate courtship displays, complex nesting behaviors, and extended parental care that rivals that of modern birds and mammals. Orodromeus and Troodon construct carefully engineered nests with temperature regulation systems that suggest advanced understanding of incubation requirements. While some theropods apparently engage in elaborate feather displays for mate attraction that parallel the courtship behaviors of modern birds. Extinction patterns throughout the Mesozoic era reveal that dinosaurian lineages show remarkable resilience to environmental perturbations that eliminate other groups, surviving multiple smaller extinction events while maintaining their ecological dominance. This evolutionary robustness suggests that the basic dinosaurian body plan and ecological strategies prove exceptionally well suited to Mesozoic environmental conditions. Yet this same specialization may ultimately contribute to their vulnerability when truly catastrophic environmental changes finally occur. And through this longest of all evolutionary experiments with large-bodied terrestrial vertebrates, dinosaurs establish ecological patterns and evolutionary innovations that will influence all subsequent terrestrial life while demonstrating that evolutionary success can be measured in temporal persistence rather than technological achievement. Their democracy of claws, teeth, and massive bodies governs continental ecosystems for longer than any other group of large animals, yet never transcends the biological constraints that keep intelligence within purely organismal rather than technological frameworks. The reign continues with geological patience, each species adding its own innovations to the dinosaurian experiment while maintaining the fundamental ecological relationships that sustain their evolutionary success across changing continental configurations and climate systems. Mammals in the margins scurry through Mesozoic undergrowth as furry shadows beneath the feet of dinosaurian giants, their small bodies and nocturnal habits concealing evolutionary innovations that will eventually reshape terrestrial ecosystems in ways that dwarf even dinosaurian ecological impact. For over 100 million years, these mouse-sized creatures perfect physiological and behavioral adaptations that remain invisible to the dominant reptilian fauna while establishing the mammalian characteristics that will prove crucial for survival in the post-dinosaur world. Metabolic innovations distinguish early mammals from their reptilian contemporaries, as these small creatures develop endothermic physiology that allows sustained activity regardless of environmental temperature. Hair evolves as an insulation system that maintains stable body temperatures during cool nights and seasonal temperature fluctuations that challenge ectothermic reptiles, while mammary glands provide nutritional independence for developing young that eliminates the vulnerability period associated with reptilian egg-laying strategies. These physiological advances prove energetically expensive, but provide competitive advantages in marginal environments where dinosaurs cannot maintain consistent activity levels. Nocturnal adaptations become highly sophisticated in early mammals as these creatures exploit temporal niches unavailable to diurnal dinosaurian communities. Enhanced hearing develops through complex middle ear structures that allow detection of high-frequency sounds, while enlarged olfactory systems provide detailed chemical information about environmental conditions in darkness, where visual systems prove inadequate. Mesozoic mammals become acoustic and chemical specialists, gathering environmental information through sensory modalities that dinosaurs largely ignore. Brain complexity increases dramatically in mammalian lineages as enhanced sensory processing requirements drive the evolution of larger, more sophisticated nervous systems relative to body size. Early mammals develop expanded cerebral cortex regions for integrating complex sensory information, while cerebellar enlargement improves motor coordination for three-dimensional movement through dense vegetation and arboreal environments. These neurological innovations establish the foundation for the advanced cognitive abilities that will characterize later mammalian evolution. Tooth diversification in Mesozoic mammals reflects sophisticated dietary specializations that allow exploitation of food resources ignored by large dinosaurian herbivores and carnivores. Multituberculates develop ever-growing teeth for processing seeds and tough plant materials, while early placentals evolve specialized dental arrangements for insectivory, small vertebrate predation, and omnivorous feeding strategies. This dental innovation creates ecological opportunities for mammals in microhabitats where body size limitations exclude dinosaurian competitors. Social behaviors emerge early in mammalian evolution as some lineages develop cooperative strategies for territory defense, predator avoidance, and resource exploitation that compensate for small individual body size through group coordination. Evidence suggests that some Mesozoic mammals engage in communal nesting, coordinated foraging, and alarm-calling systems that demonstrate sophisticated communication abilities. These early social systems establish behavioral foundations that will prove crucial for the complex mammalian societies that evolve after dinosaurian extinction. The mystery of mammalian ecological suppression during the Mesozoic era involves understanding why these innovative creatures remain small and ecologically marginal, despite possessing physiological and behavioral advantages that should favor ecological expansion. Dinosaurian dominance apparently creates competitive exclusion that prevents mammalian exploration of larger body sizes and more diverse ecological roles, suggesting that evolutionary innovation alone cannot overcome established ecological dominance by incumbent groups. Reproductive strategies in early mammals involve increasingly sophisticated approaches to offspring care that provide survival advantages in environments where predation pressure from dinosaurs remains intense. Live birth eliminates the vulnerability associated with external eggs, while extended parental care allows transmission of learned behaviors and survival strategies to offspring. Lactation provides high-quality nutrition that supports rapid growth rates and brain development in young mammals, creating energetic investments in offspring quality rather than quantity. Arboreal adaptations develop in multiple mammalian lineages as these creatures discover three-dimensional habitat niches in forest canopies where large dinosaurs cannot follow. Prehensile tails, grasping hands and feet, and enhanced proprioception for maintaining balance while moving through complex three-dimensional environments all evolved during the Mesozoic era. These arboreal innovations establish locomotor patterns that will prove crucial for primate evolution and eventual human technological development. Hibernation and torpor evolve as energy conservation strategies that allow mammals to survive seasonal food shortages and harsh environmental conditions that force continuous activity in ectothermic reptiles. These physiological adaptations to resource limitation provide mammals with survival advantages during environmental perturbations, while reducing competition with dinosaurs during periods when reptilian activity levels decline. Metabolic flexibility becomes a key mammalian innovation that enhances survival in unstable environments. Placental reproduction emerges during the Cretaceous period as some mammalian lineages develop sophisticated internal gestation that provides developing embryos with optimal nutritional and protective environments. The placental connection between mother and offspring represents one of evolution's most intimate physiological relationships, allowing precise control over fetal development while providing immunological protection and nutritional support. This reproductive innovation proves so successful that placental mammals will eventually dominate most terrestrial ecosystems. Sensory specialization reaches extraordinary levels in different mammalian lineages as these creatures partition acoustic and chemical environments in ways that reduce competition while maximizing information gathering efficiency. Some early mammals develop echolocation abilities for navigation and prey detection in complete darkness, while others evolve enhanced chemical communication systems for territory marking and mate recognition. These sensory innovations create communication channels largely invisible to dinosaurian predators and competitors. Geographic distribution patterns suggest that early mammals achieve greater dispersal success than many dinosaurian lineages, possibly due to their small body size, metabolic flexibility, and ability to exploit temporary food resources during migration. Mammalian fossils appear on multiple continents during the Mesozoic era, indicating successful colonization of diverse environments despite their ecological marginality. This dispersal ability may contribute to mammalian survival through the end Cretaceous extinction event. Digestive innovations allow early mammals to extract nutrients from food sources that larger dinosaurs cannot efficiently process, creating dietary niches based on food particle size rather than total food availability. Complex stomach arrangements, specialized gut bacteria, and sophisticated food processing behaviors all emerge in different mammalian lineages, allowing exploitation of insects, seeds, nectar, and other small-scale food resources that require precise manipulation rather than bulk consumption. Thermoregulatory sophistication in early mammals involves not just metabolic heat production, but also behavioral and physiological mechanisms for preventing overheating in warm Mesozoic climates. Countercurrent heat exchange systems, behavioral thermoregulation through burrowing and shade-seeking, and physiological adjustments to heat stress all develop as mammals learn to manage the energetic costs of endothermy in environments where excessive heat poses greater challenges than cold stress. Evolutionary rates appear to accelerate in mammalian lineages relative to contemporary dinosaurs, with morphological and ecological diversification occurring more rapidly in small-bodied mammalian clades than in established dinosaurian groups. This evolutionary acceleration may result from shorter generation times, higher mutation rates, or relaxed developmental constraints in small-bodied organisms, creating rapid evolutionary responses to environmental changes and ecological opportunities. And through these millions of years in ecological shadows, mammals develop the physiological, behavioral, and ecological innovations that will prove essential for survival and eventual dominance in post-dinosaurian ecosystems. Their marginal existence during the Mesozoic era proves deceptive, concealing evolutionary experiments that establish the foundations for complex mammalian societies, advanced cognitive abilities, and eventually the technological innovations that will transform the nature of life on Earth. The small forms persist with quiet determination, each species adding incremental innovations to the mammalian toolkit while waiting for environmental changes that will create opportunities for ecological expansion. Their patient preparation in the margins sets the stage for one of evolution's most dramatic reversals of fortune. The recent experiment begins with ice sheets advancing and retreating across continents in rhythmic cycles that have governed global climate for the past 3 million years, creating environmental pressures that drive the evolution of increasingly sophisticated hominid lineages. These Pleistocene glaciations represent Earth's latest experiment with climate instability, alternating between ice ages that lock vast amounts of water in continental glaciers and interglacial periods that create briefly favorable conditions for technological innovation. Against this backdrop of climatic upheaval, a lineage of African apes begins the improbable journey toward language, agriculture, and industrial civilization. Australopithecus emerges on East African savannas roughly 4 million years ago as climate change transforms dense forests into open grasslands, creating ecological pressures that favor bipedalism, tool use, and increasingly sophisticated social behaviors. These early hominids develop upright locomotion that frees their hands for manipulation while maintaining the brain sizes of modern chimpanzees, suggesting that technological innovation precedes rather than follows cognitive enhancement. The transition from arboreal to terrestrial life represents one of evolution's most consequential experiments with primate ecology. Stone tool technology appears in the archaeological record 2.6 million years ago as Homo habilis begins systematic modification of rock fragments to create cutting and scraping implements that extend the capabilities of biological anatomy. These early tools represent humanity's first steps toward technological augmentation of natural capabilities, establishing patterns of environmental manipulation through artificial objects that will eventually encompass everything from fire control to space exploration. The cognitive leap required for systematic tool manufacture marks the beginning of culture as an evolutionary force. Brain expansion accelerates in hominid lineages throughout the Pleistocene epoch as cranial capacity increases from roughly 400 cubic centimeters in early Australopithecines to over 400 cubic centimeters in modern humans. This neurological enhancement occurs alongside increasingly sophisticated tool technologies, complex social organizations, and elaborate symbolic behaviors that suggest feedback loops between cultural innovation and biological evolution. The energetic costs of maintaining large brains require corresponding improvements in food processing efficiency and social cooperation. Fire control emerges sometime between 400,000 and 800,000 years ago, as early humans learned to maintain, transport, and eventually kindle flames that extend their ecological niche into previously uninhabitable environments. Controlled fire provides warmth for survival in temperate and Arctic regions, enables cooking that improves nutritional extraction from food, and creates social focal points that may facilitate language development and cultural transmission. This mastery of combustion represents humanity's first major manipulation of chemical energy sources. Language evolution remains one of the most mysterious aspects of human development, with sophisticated communication systems apparently emerging sometime within the past 200,000 years as anatomically modern humans develop the physiological and neurological capabilities for complex vocal communication. The evolution of recursive grammar, abstract symbolic reference, and cultural transmission through verbal instruction creates unprecedented mechanisms for accumulating and sharing information across generations. Language transforms human societies from collections of individuals into collective intelligence systems. Agricultural revolution begins approximately 10,000 years ago as human populations in multiple regions independently develop techniques for domesticating plants and animals, fundamentally altering the relationship between human societies and natural ecosystems. The transition from hunting and gathering to food production supports larger population densities while creating social stratification, permanent settlements, and specialized labor roles that establish the foundations for complex civilizations. Agriculture represents humanity's first systematic modification of ecological systems for enhanced resource production. Metallurgy develops as human societies learn to extract and manipulate metals from mineral ores, beginning with copper working around 7,000 years ago and progressing through bronze and iron technologies that create increasingly sophisticated tools, weapons, and artistic objects. The ability to transform raw materials through controlled heating and chemical processes demonstrates increasingly sophisticated understanding of material properties and transformation principles. Metal technology establishes patterns of resource extraction and environmental modification that will characterize all subsequent technological development. Writing systems emerge in multiple civilizations as human societies develop methods for recording and transmitting information through symbolic representation, creating external memory systems that allow cultural knowledge to accumulate beyond the limits of individual human memory. The invention of writing transforms human societies from primarily oral cultures to literate civilizations capable of maintaining complex administrative systems, preserving historical records, and coordinating activities across large populations and extended time periods. Scientific method evolves during the past several centuries as human investigation of natural phenomena becomes increasingly systematic, experimental, and mathematical, creating knowledge-gathering techniques that accelerate the pace of technological innovation and environmental understanding. The development of controlled experimentation, mathematical modeling, and peer review creates cultural mechanisms for testing and refining ideas about natural processes. Science establishes humanity's most powerful method for understanding and manipulating natural systems. Industrial Revolution transforms human societies beginning in the 18th century as fossil fuel combustion powers mechanical systems that multiply human productive capabilities by orders of magnitude. The harnessing of coal, oil, and natural gas energy sources enables massive increases in manufacturing output, transportation capacity, and environmental modification while supporting human population growth that reaches levels unprecedented in any other large mammal species. Industry represents humanity's transition from biological to technological energy sources. The mystery of human uniqueness involves understanding why this particular lineage of African apes develops technological civilization while other intelligent animals, dolphins, elephants, great apes remain within purely biological frameworks, despite possessing sophisticated cognitive abilities and complex social systems. The combination of bipedalism, manual dexterity, vocal communication, and social cooperation apparently creates a unique evolutionary trajectory that enables cumulative cultural evolution and technological innovation. Global environmental impact of human activities reaches planetary scales as industrial civilization begins to influence atmospheric composition, ocean chemistry, and biological diversity at levels comparable to major geological forces. Human carbon dioxide emissions alter global climate patterns, while agricultural and urban development transforms continental landscapes and drives extinction rates that approach those of major mass extinction events. The human experiment with technological civilization creates environmental changes that operate on geological timescales. Population dynamics in human societies differ dramatically from those of other large mammals, as technological innovations repeatedly overcome resource limitations that would normally constrain population growth through Malthusian mechanisms. Medical advances, agricultural improvements, and energy technologies allow human populations to reach levels that would be unsustainable without continuous technological innovation. Human demography operates according to cultural rather than purely biological principles. Communication technologies evolve from basic writing systems to global information networks that connect human societies across all continents and enable real-time coordination of activities on planetary scales. The development of printing, telecommunications, and digital information systems creates collective intelligence capabilities that far exceed the cognitive capacity of individual humans. Information technology establishes humanity's most sophisticated method for coordinating complex social behaviors. Space exploration represents humanity's most recent experiment with extending technological capabilities beyond Earth's surface, establishing the principle that human societies can develop technologies capable of operating in environments completely unlike those in which they evolved. The ability to send mechanical systems to other planets and maintain human presence in orbital environments demonstrates technological capabilities that transcend the biological constraints that limit all other terrestrial organisms. And through this recent experiment with technological intelligence, Earth witnesses the emergence of the first known civilization capable of understanding its own evolutionary history, manipulating global environmental systems, and potentially extending life beyond planetary boundaries. The human lineage represents evolution's most dramatic experiment with intelligence-driven environmental modification, creating possibilities and challenges that have no precedent in the 4-billion-year history of life on Earth. The experiment continues with characteristic human restlessness, each generation adding new technologies and social innovations while grappling with the consequences of capabilities that evolve faster than wisdom. The recent arrival of technological civilization creates questions about sustainability, planetary stewardship, and the long-term trajectory of intelligence in the universe that remain unanswered as the human story unfolds against the vast backdrop of cosmic time. And so, the question that began this journey, what if we're not the first civilization on Earth, finds its answer not in hidden ruins or lost technologies, but in the patient record of stone and fossil that speaks of deep time's experiments with complexity. 4.5 billion years of planetary evolution reveal countless forms of organization, intelligence, and environmental modification, yet none that approach the particular combination of characteristics that define technological civilization as humans understand it. The trilobites engineered sophisticated optical systems from living crystal, but never learned to make fire. Dinosaurs ruled continental ecosystems for 3 times longer than mammals have existed, developing social behaviors and cognitive capabilities that rivaled those of modern birds, yet never transcended the biological framework of their reptilian inheritance. Carboniferous forests created the first planetary-scale ecosystem engineering projects, transforming atmospheric composition and climate through photosynthetic industry, but operated according to biological rather than technological principles. Each geological epoch reveals Earth experimenting with different approaches to complexity and environmental modification, testing the boundaries of what life can achieve within the constraints of physics, chemistry, and evolutionary possibility. The bacterial innovations that oxygenated ancient atmospheres represent environmental engineering on scales that dwarf human industrial capacity. The flowering plants that diversified during the Cretaceous period demonstrate sophisticated chemical communication and ecosystem modification that continues to shape global environmental systems. Yet something about the particular trajectory that led to human technological civilization appears to be genuinely unprecedented in Earth's long history. The combination of bipedalism, manual dexterity, vocal communication, and social cooperation that characterizes human evolution creates possibilities for cumulative cultural development that other intelligent lineages never achieved. The archaeological and fossil records preserve no evidence of earlier experiments with controlled fire, systematic tool manufacture, or symbolic communication systems that approach human technological sophistication. Perhaps the constraints that prevented earlier civilizations involve the particular sequence of environmental conditions that shaped human evolution, the climate instability of the Pleistocene, the geographic isolation of African populations, the specific ecological pressures that favored technological innovation over purely biological adaptation, or perhaps the transition from biological to technological intelligence requires such an improbable combination of circumstances that it occurs very rarely in evolutionary history, making human civilization a genuine singularity in Earth's 4-billion-year experiment with life. The rocks continue their slow testimony, each layer recording another chapter in the story of life's relationship with planetary systems. Ice cores preserve atmospheric histories that stretch back hundreds of thousands of years. Sedimentary deposits contain chemical signatures of ancient ecosystems and climate conditions. The geological record offers humanity a perspective on its own existence that encompasses timescales far beyond human experience, revealing both the uniqueness and the deep continuity of Earth's evolutionary experiments. In this context, human civilization emerges not as the inevitable result of evolutionary progress, but as the latest and perhaps most improbable chapter in Earth's ongoing exploration of what life can become when given sufficient time and opportunity for experimentation. The question shifts from whether we are the first technological civilization to whether the particular form of intelligence and environmental modification that humans represent can establish sustainable relationships with the planetary systems that gave rise to it. The ancient Earth sleeps beneath modern cities and agricultural landscapes, its deep time dreams accessible only through the patient work of scientists who read the stories written in stone and fossil. 4.5 billion years of planetary history provide the foundation for 3 million years of human evolution, which in turn support the 10,000 years of agricultural civilization that create the context for the few centuries of industrial development that shape the modern world. The wind moves across landscapes that have witnessed the rise and fall of countless ecosystems, carrying molecules that have participated in billions of years of chemical cycling between atmosphere, ocean, and living systems. Each breath connects modern organisms to the ancient metabolisms that first learned to harness solar energy, process atmospheric gases, and build complex organic structures from simple mineral components. The silence of deep time continues its patient measurement of change, marking the rhythms of geological processes, evolutionary innovation, and ecological transformation that operate on timescales far beyond human perception. In this vast temporal context, the human experiment with technological civilization represents just the latest moment in Earth's continuing exploration of complexity, intelligence, and environmental modification. The planet turns through space, carrying its cargo of living experiments through another day in the cosmic story that began with the formation of the solar system and continues toward futures that remain unwritten in stone, unknown to fossil, and open to possibilities that 4.5 billion years of evolutionary creativity have only begun to explore. Sleep well in the knowledge of deep time, where every moment extends backward through eons of preparation and forward through ages of potential yet to be discovered.